Welcome in, everyone. We are embarking on a mission today that is honestly unlike anything we've ever attempted on this show.
Truly, it's a massive undertaking.
Yeah, and you, the listener, you're sitting right here with us.
Yeah.
You are the third person in the room for a very specific, highly rigorous deep dive.
Right.
Our objective is to rigorously, line by line, deconstruct this breathtaking moment in mathematical and computational history. We're looking at a document titled Claude's Cycles.
Written by the legendary computer scientist Don Knuth.
Exactly. It's dated February 28, 2026, with revisions up to March 6, 2026. And, this document captures the exact moment a world-renowned pioneer realizes that an open combinatorial problem he was wrestling with was just solved by an artificial intelligence.
It is a milestone document. I mean, to properly respect the magnitude of this text, we are going to be operating under what we're calling the unabridged protocol.
Yes, the unabridged protocol.
This means we process Don Knuth's document strictly in linear order. We will not skip a single sentence. We will not summarize broadly where specifics are provided.
No skipping.
We read chronologically, unpack every mathematical concept at a foundational level, and leave absolutely no stone unturned. And to ensure absolute rigor, after every single paragraph or complex formula, we will execute a completeness check, just to verify we've extracted every ounce of meaning before moving forward.
Exactly. So we are assuming we have infinite time today. But before we hit the first line of the text, we really need to set the stage for you. Knuth mentions this problem came up while writing for The Art of Computer Programming.
Right, TAOCP.
Yeah. Now, for an advanced audience, we know TAOCP is the foundational text of algorithms. But let's really dig into why an open problem from Donald Knuth, specifically in this era of his writing, carries so much weight in the theoretical computer science community.
I would be delighted to unpack that. I mean, The Art of Computer Programming isn't just a textbook. It's an attempt to catalog the entirety of fundamental algorithmic knowledge. He started it in 1962.
Wow.
Yeah. Volumes 1 through 3 covered fundamental algorithms, semi-numerical algorithms, sorting, and searching. But for the last few decades, he has been entirely consumed by Volume 4.
And that one deals with combinatorial algorithms, right?
Precisely. Combinatorics is the mathematics of counting, arranging, and searching through discrete structures. So when Knuth poses an open problem in the drafts of Volume 4, it means he has mapped out the known universe of a specific discrete structure, like a graph or a tree, and he's found a dark corner where classical algorithmic theory just breaks down.
It's the absolute boundary.
It represents a boundary of our current algorithmic understanding. For an AI to step over that boundary and solve it, especially an AI not explicitly hard-coded with a solution by a human, well, it forces us to reconsider the epistemological limits of machine deduction.
That covers the introduction to our deep dive.
Yeah.
Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the first paragraph of Knuth's text.
All right, paragraph 1. It begins with the title and author. Claude Cycles, Don Knuth, Stanford Computer Science Department, 28 February 2026. Revised 06, March 2026.
Okay.
Then he writes, shock. I learned yesterday that an open problem I'd been working on for several weeks had just been solved by Claude Opus 4.6 Anthropic's hybrid reasoning model that had been released 3 weeks earlier.
Let's pause on the rhetorical impact of those first two words. Shock.
Yeah, that's huge coming from him.
It is immense. Here is a man who essentially laid the mathematical bedrock for how computers process information. He's notoriously skeptical of tech industry fads, and he's admitting total astonishment.
And he specifically names the AI model, right?
Yeah.
Noting it is a hybrid reasoning model.
That is a crucial distinction. By early 2026, AI had evolved past simple next token prediction, the classic autoregressive transformer architecture.
Right.
These were now systems capable of structured, multi-step logical deduction. They used internal scratch pads and reinforcement learning from human feedback, specifically tuned for mathematical reasoning.
He goes on in the paragraph to say, it seems that I'll have to revise my opinions about generative AI one of these days. What a joy it is to learn not only that my conjecture has a nice solution, but also to celebrate this dramatic advance in automatic deduction and creative problem solving. I'll try to tell the story briefly in this note.
His admission that he must revise his opinions is a powerful testament to you, the listener, about the inflection point we reached in human-machine collaboration.
He's not defensive at all.
Not at all. He calls it a joy.
Yeah.
He is celebrating the advance of automatic deduction because, at his core, Knuth is a lover of pure combinatorial problem solving, regardless of the solver's substrate.
That covers the first paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 2. Knuth writes, here's the problem, which came up while I was writing about directed Hamiltonian cycles for a future volume of The Art of Computer Programming.
Okay, we should pause here. We all know basic graph theory, but let's deeply contextualize why finding directed Hamiltonian cycles is such a vicious computational barrier.
Yeah. Why is it so hard?
It comes down to computational complexity. Finding a Eulerian path, a path that visits every edge exactly once, is computationally trivial. You just check the degrees of the vertices. Euler solved that in the 1700s.
Right, the bridges of Königsberg.
Exactly. But finding a Hamiltonian cycle, a path that visits every single vertex exactly once, is classified as NP-complete for general graphs.
Meaning there's no shortcut.
There is no known local property you can check to guarantee a Hamiltonian cycle exists. You essentially have to search the global structure of the graph. As the graph grows, the state space of possible paths explodes factorially.
It gets overwhelmingly massive.
Any problem involving the generalized decomposition of Hamiltonian cycles immediately signals that we are dealing with a search space that will choke the largest supercomputers on Earth if you attack it with blind brute force.
That covers the preamble to the problem definition. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Now we hit the dense mathematics. Remember our perfect pronunciation protocol for this. Knuth defines the problem. Consider the digraph with the number of vertices, aiming for $3 mere cubed vertices.
Let's break that down immediately. A digraph is a directed graph, meaning the edges have arrows, they point one way, and the total number of points in this universe is the number of vertices, m $3 meter cubed.
So it's a three-dimensional space, he continues. The vertex labels m, t, l, sever I, j, k, l, I, m, and u, g for 0, is less than or equal to I, j, and k, which are strictly less than m.
Right. This constraint means we are operating in a bounded integer lattice. You have three coordinates, I, j, and k, and they run from 0 up to m minus 1.
He just goes, and 3 arcs from each vertex, namely to the first directed arc, m plus jk ad lod idle, I plus jk, the second directed arc, a l lable ij plus k, and the third directed arc, ajk plus the modulo operation, a plus t plus I with a plus 1, m plus m, I plus equals the quantity I plus 1 modulo m. Let's really dive deep into the topology of this space.
This is a beautifully constructed mathematical arena. From any vertex, you can only move strictly positively along one of the three axes. You step forward on I, or forward on j, or forward on k.
But because Knuth explicitly defines those movements, using the modulo operation, Hanna plus I plus 1, g mod m to I plus equals the quantity I plus 1 modulo m, we aren't dealing with a standard bounded cube, are we?
No, we are dealing with a three-torus, a toroidal topology. Because of the modulo operation, the space wraps around on itself. If you are at the maximum coordinate, m minus 1, and you move forward, you seamlessly loop back to 0.
Like reaching the edge of a screen in an old video game and appearing on the other side.
Exactly like that. Removing the edge boundaries is what makes finding these Hamiltonian cycles so vicious, because you have perfect structural symmetry.
Right.
There are no corners, no dead ends to anchor your search algorithm. Every single vertex in this space looks exactly identical to every other vertex locally.
It's a 3 regular directed graph on a torus. At every intersection, you face 3 identical choices.
Yeah.
Knuth concludes the second paragraph with the actual challenge. Try to find a general decomposition of the arcs into 3 directed, the cycle length, 3 other meter cube cycles for all meter 2. Let's rigorously define general decomposition here. Why is this so hard?
Well, a decomposition of a graph means partitioning its edge set. Because every vertex has an out degree of exactly 3, there are precisely 3 times m cubed total directed edges in this entire torus.
Okay.
Knuth is demanding that we partition this massive set of edges into exactly 3 distinct subsets. The constraint is that each subset, if followed exclusively, must form a valid, unbroken Hamiltonian cycle.
A continuous loop of length.
Yeah.
The cycle length, 3 meter cubed, that touches every single vertex exactly once.
Exactly. This means that every single coordinate ijk, you must assign one outgoing direction to cycle 1, one to cycle 2, and one to cycle 3, without ever creating a subloop or missing a vertex across the entire global space.
And the final constraint. For all M2, he doesn't just want one solution for a specific grid size.
No, he wants a universal mathematical theorem that generates these perfect decompositions for any arbitrarily large torus.
That covers the mathematical definition of the digraph in the second paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 3. Knuth writes, I had solved the problem for MEG3, and asked for a generalization as part of the answer to an exercise in 3. My friend Philip Stappers rose to the challenge and empirically discovered solutions for 4-3. The inequality bounds, 1 led 3, is less than or equal to m, which is less than or equal to 16. Therefore, it became highly likely that the desired decompositions do exist, except when m, the inequality constraint, is less than or equal to 2.
This paragraph serves a vital rhetorical purpose. It establishes the limits of human computational perseverance before introducing the AI. Knuth, with his unparalleled combinatorial intuition, solved the m equals 3 case. That's a state space of 27 vertices.
Which is doable for a genius by hand.
Right. Then Philip Stappers pushed the empirical boundary. He likely wrote highly optimized backtracking SAT solvers to find instances up to m equals 16.
And for m equals 16, we're looking at 4,096 vertices.
Exactly. Finding 3 perfectly interwoven Hamiltonian cycles in a space of 4,096 vertices is an immense empirical achievement. But in mathematics, empirical existence is not a mathematical proof.
You just have the artifacts, right?
Yes. Computing solutions for a consecutive string of integers gives you a strong heuristic prior that a universal pattern must exist. But you still don't have the rule.
That covers the 3rd paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Moving to section 2 of our deep dive. The coaching and initial explorations. Paragraph 4. Indeed, it was Philip who had the gumption to pose this question to Claude, using exactly the wording above. He also gave guidance coaching, instructing Claude to summarize its ongoing progress. Then he quotes Stappers' exact prompt. After every explore apply run, immediately update this file plan.md before doing anything else. No exceptions. Do not start the next exploration until the previous one is documented here.
I absolutely love this detail.
Yeah, Stappers is dealing with Opus 4.6, one of the most advanced reasoning engines on Earth, and he basically has to treat it like a brilliant but completely scatterbrained intern.
Write down what you did before you do the next thing, no exceptions. It speaks volumes about the architecture of LLMs in 2026.
Why is this strict scaffolding necessary for LLM reasoning?
The machine can navigate a multidimensional search space, but it suffers from severe context window degradation and catastrophic forgetting during long-horizon tasks. An LLM's memory is simply its context window.
Right, it doesn't really learn on the fly.
Exactly. By forcing the AI to explicitly write its hypotheses, empirical results, and failures into a static markdown file, Stappers is artificially engineering an external working memory. This technique, often called scaffolding or chain of thought preservation, forces the model to re-ingest its own structured logic at the start of every new interaction. He is preventing the AI from looping through the same failed combinatorial branches.
That covers the 4th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 5 shows Claude's immediate mathematical pivot. And Claude's plan of attack was quite admirable. First, it reformulated the problem. Need the mapping function, sigma, zm3 to s33, the function sigma mapping z sub m cubed to s sub 3, assigning a permutation of 0, 1, 2 at each vertex. Cycle C at vertex v goes in direction sigma vc. Each resulting functional digraph must be a single Hamiltonian cycle.
Let's contextualize how profound this pivot is. By translating a routing problem into the symmetric group S sub 3, Claude is moving from pure graph theory combinatorics into abstract algebra.
This is the hallmark of mathematical maturity, isn't it?
It truly is. Claude refuses to look at this as a messy web of 3-meter-cubed arrows. Instead, it defines the domain space as the set of integers modulo m, zevni m3, z sub m cubed. This formalizes the 3 torus geometry perfectly.
And then it maps every point in that space to a codomain, which is the symmetric group 3 sub 3.
Yes. For you listening, S sub 3 is the symmetric group of degree 3, representing all possible permutations of 3 distinct elements. There are exactly 3 factorial or 6 elements in this group.
So the identity, 3 transpositions, and 2 3 cycles.
Exactly. What Claude is saying is, I do not need to route individual lines. I simply need to assign one of these 6 rigid permutation templates to every single coordinate. It compresses the action space from choosing individual edges to choosing a unified routing state at each vertex.
Knuth continues in the same paragraph. Then it tried for a simple answer. If sigma is cyclic, i.e., the cycle function fcv, c plus gv, v mod 33, s sub c of v equals the quantity c plus g of v modulo 3 for some. The function g, zm3 to zd33, the function g mapping z sub m cubed to z sub 3, then we only need one function g. Tested linear, The linear function g, the Allegro rollers, ac dot I plus z dot I j plus c dot g plus theta 3 3. G equals the quantity a times I plus b times t plus c times k modulo 3 in quadratic variants. No linear or simple quadratic g works.
Here, Claude is applying Occam's razor. It's looking for the most elegant possible algebraic solution. It postulates that maybe the choice of permutation is driven by a simple cyclic shift dictated by a global function g.
So it tests linear mappings.
Right. Essentially asking, if I draw a straight line through this 3D torus, does the routing template change uniformly along that line? It tests it computationally, likely calculating the kernel of that linear transformation, and proves it fails.
Then it bumps the polynomial degree to quadratic, searching for parabolic symmetries.
And those fail too. The AI is systematically proving that the solution requires a higher degree of nonlinear complexity.
That covers the 5th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 6. Knuth writes, Claude's second exploration was what it called a DFS search attempt, depth-first search, attempted brute force DFS over sigma assignments for m equals 3. The exponential search space, 6 taller size, and 6 to the power of 27 search space. Too slow without good pruning.
It's almost comical that the AI tried to brute force a 6 to the power of 27 search space. It is the algorithmic equivalent of touching a hot stove to confirm it's hot.
Yeah, exactly. Why is the depth-first search so bad here?
A depth-first search explores a branch of a decision tree down to its absolute end before backtracking. In this case, at each of the 27 vertices of the m equals 3 graph, the AI must choose one of the 6 permutations from S sub 3. Thus, the state space is the exponential search space, 60 Mozilla 6 to the power of 27.
Which is roughly 10 to the 21st power.
A monstrous number. Even if you can evaluate a billion complete graph colorings per second, it would take you hundreds of thousands of years to traverse that tree.
So Claude writes the script, runs it, watches the execution time stall indefinitely, and correctly concludes, too slow without good pruning.
Right. Pruning refers to branch and bound techniques, where you mathematically prove a certain branch of the tree cannot possibly contain a valid solution, so you cut it off early. But Claude realizes it doesn't have the heuristics to prune effectively yet.
That covers the 6th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 7 introduces a leap in strategy. Knuth writes, thirdly, it tried what it called 2D serpentine analysis. Key 2D result, the pattern, the two-dimensional pattern, 0 Mullins into 1 Mullers, the sequence consisting of 0 repeated m minus 1 times, followed by 1, all repeated m times, gives a Hamiltonian cycle in the Cayley graph, 6 zm2, E1, the Cayley graph of z sub m squared with generators E0 and E1 for m for 3. Its complement also works, giving a valid 2D decomposition.
This is fascinating.
When the text says Claude recognized this as a Cayley digraph, is that true mathematical intuition? Or is the AI just probabilistically regurgitating group theory Wikipedia pages because the words grid and cycle were in its context window?
That is the defining question of AI research in this era. A Cayley graph is a construct that encodes the abstract structure of a mathematical group into a geometric graph. The generators E0 and E1 represent the fundamental transformations moving along the x-axis or y-axis.
So by identifying the 2D grid specifically as the Cayley graph, CM2, the Cayley graph of z sub m squared with generators E0 and E1, Claude is linking the geometric problem to algebraic group theory.
Precisely. Whether it truly understands this or is just mapping latent space vectors is philosophically debatable, but functionally irrelevant. The output is mathematically profound. To solve the impenetrable 3D problem, it drops a dimension.
It goes flat.
Yes. It finds a serpentine sequence. Move straight m minus 1 times, then turn once, and repeat that entire sequence m times. It perfectly weaves through a 2D torus.
That covers the 7th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 8. Knuth writes, exploration number 4 constructed the 3D serpentine pattern. The 3D pattern with typo 0 was the 0 repeated m minus 1 times, followed by 1, all repeated m minus 1 times, followed by the sequence 0 repeated m minus 1 times, followed by 2, all repeated m times. That's a typographic error. For the corrected 3D pattern, 0 repeated m minus 1 times this one dix, the sequence consisting of the subsequence 0 repeated m minus 1 times, followed by 1, repeated m minus 1 times, followed by 0 repeated m minus 1 times, followed by 2, all repeated m times. It's a classical sequence called the modular M-Mary Gray code on page 299 of 2.
This is a fascinating moment of hallucination versus structure.
It really is. Claude attempts to extrude its 2D snake into a 3D snake. It generates a complex sequence notation, but it drops a bracket. The syntax is broken.
Yet Knuth looks at the broken syntax and immediately recognizes the semantic intent. The AI was trying to generate a modular M-ary gray code.
And what exactly is a gray code for the listener?
A traditional gray code is a binary sequence where two successive values differ in only one bit, often used in error correction to prevent transient states. A modular M-ary gray code extends this to base M numbering.
So geometrically, it represents a path through an m-dimensional grid that visits every point, changing only one coordinate at a time.
Exactly. The AI hallucinated a typo, but it hallucinated the correct, highly advanced structural concept.
Knuth finishes that paragraph with, after deleting this cycle from the graph, Claude looked at the remaining two regular digraph and found that it has rigid structure, making decomposition difficult.
Right. Once you map that massive 3D gray code sequence and extract it from the graph, you consume one outgoing edge from every single vertex. You are left with a two regular digraph. Every vertex now only has two choices instead of three.
The options are shrinking.
And Claude analyzes this residual mathematical scaffolding and realizes it is too constrained. The remaining edges are trapped in interlocking local cycles that cannot be joined into two massive global Hamiltonian loops. The 3D serpentine was a brilliant geometric hypothesis, but it fundamentally breaks the graph for the remaining cycles.
That covers the 8th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 9. Knuth writes, nevertheless, exploration number 5 analyzed that residual digraph, finding some cycles. Unfortunately, they didn't work out.
This is just a brief procedural update, really showing the rigorous diligence of the AI. It didn't just guess the residual graph was rigid. It ran cycle-finding algorithms, likely employing components of Tarjan's strongly connected components algorithm to map the leftovers.
So it computationally verified the dead end before moving on.
Exactly.
That covers the 9th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Now we enter section 3, the fiber framework breakthrough, paragraph 10. Back to the drawing board. Several other approaches were tried. For example, looking at the choices to be made at vertices that lie on the hyperplane, where I plus j plus k is congruent to 1. Nothing promising showed up until exploration number 15, which introduced what Claude called a fiber decomposition. The quotient map function SIJK FR plus K plus I plus J plus J plus K plus B modulo M maps all arcs from fiber. The fiber set 5 over set 7 subs to the next fiber set 5 over set 5 is subsub F sub S plus 1. The digraph is layered in fiber coordinates ij with the k coordinate derived k FL equals a quantity S minus I minus J modulo M.
This is the inflection point of the entire search.
Let's dig deeply into what a hyperplane and a fiber map are in discrete geometry.
The AI stops trying to visualize the three torus as a tangled web of coordinates and shifts to a fine geometry. A hyperplane in a three-dimensional space is essentially a flat two-dimensional slice cutting through the volume. Initially, it looked at the specific hyperplane where the sum of the coordinates equals minus 1 modulo m.
But that didn't yield a pattern.
No. But then it abstracts the concept completely. It defines a quotient map, simply adding the three coordinates together modulo m. This function creates equivalence classes. Every single point in the space where I plus j plus k evaluates to 0 belongs to fiber f sub naught. Every point where the sum is 1 belongs to fiber f sub 1, and so on.
And the genius here is how the directed edges behave relative to these slices, right?
Exactly. Think about the allowed movements. You can increment I, j, or k by exactly 1. No matter which of the three directions you choose, the total sum of the coordinates will increase by exactly 1.
So every single directed edge must point from a vertex in fiber f sub s strictly to a vertex in fiber s sub plus 1.
Yes. Claude has completely reimagined the topology. It is no longer a torus of points. It is a perfectly ordered, repeating stack of 2D layers. The problem is now a matter of navigating gracefully from one layer to the next.
That covers the 10th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 11. Knuth quotes Claude's realization based on this new geometry. Using those fiber coordinates, the problem could now be reformulated as choosing, for each IJS, a permutation of the three operators that shift IJ by either 1, 0, 0, 1 or 0A.
This implies a continuous state space reduction, which is insane for an LLM to intuit.
It really is a massive dimensional reduction.
Yeah.
Because the sum inherently defines the current layer, the AI realizes the third coordinate k is mathematically redundant.
As the equation showed, if you know the layer S and you know I and J, you can deterministically calculate. The k-coordinate derived, k Sij b mod m omne, k equals the quantity s minus I minus j modulo m. So the AI compresses the state space from 3D coordinates to 2D coordinates embedded in a layer framework.
The routing decision is now just a choice of how to manipulate the 2D plane. You either shift I, which is vector 1, 0, shift j, vector 0, 1, or shift neither, which implicitly means you must have shifted k to reach the next layer, which is vector 0, 0.
Precisely.
Knuth finishes the paragraph. Tried sigma, depending only on fiber index s, rotation by s, gives the failing pattern, I plus j plus k b mod 3, 3, the quantity I plus j plus k modulo 3 pattern, which doesn't work. Random local search found solutions for m equals 3, but no general pattern emerged.
Having built this elegant fiber framework, Claude tests the most simplistic hypothesis. What if the routing permutation relies only on the layer you are in? Meaning every point in layer 0 executes the exact same permutation, regardless of its I or j coordinates.
It tests the algebraic pattern, and it creates closed subloops, failing the Hamiltonian constraint.
It then unleashes a random local search, a stochastic hill climbing algorithm, which finds isolated solutions for the small m equals 3 case, but the variance is too high. The fiber concept is brilliant, but it needs a more sophisticated internal logic.
That covers the 11th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 12. Exploration 18 implemented the full fiber framework as executable code. Exhaustive backtracking for m from b equals 3 found a valid decomposition in 0.1's 10932 nodes. In this solution, the permutation signal was the same for all ij in fiber SL00. A similarly uniform fiber was found for m equals 4 by simulated annealing as part of exploration 20.
Let's contrast exhaustive backtracking with simulated annealing here.
Yeah, that's an important distinction.
Exhaustive backtracking is our old friend depth-first search, but now heavily weaponized. Remember the initial 6 to the power of 27 search space that choked the machine? By applying the dimensional reduction of the fiber framework, Claude pruned the search space so aggressively that the m equals 3 case was solved in 1/10 of a second.
Exploring only 10,932 nodes.
And within that rapid solution, it spotted a profound structural anomaly. For the very first layer, where s equals 0, the permutation was entirely uniform. Every point did the same thing. But for m equals 4, the search space is still too large for backtracking, so Claude deploys simulated annealing.
Simulated annealing. That's a fascinating choice by the AI. It's borrowing from statistical mechanics, letting the search algorithm make wild, high-temperature probabilistic leaps early on to escape local minima, and then cooling it down to zero in on the exact uniform fiber.
Precisely. Simulated annealing relies on the Metropolis Hastings algorithm. It randomly mutates the graph coloring. If the mutation reduces the number of disconnected cycles, making it closer to a Hamiltonian path, it accepts it. If it makes it worse, it still might accept it with a probability proportional to the temperature.
So as the system cools, it stops accepting bad moves and converges.
Claude uses this sophisticated probabilistic engine to prove that the uniform fiber concept isn't just a quirk of m equals 3, it also holds for m equals 4. A universal mathematical law is slowly crystallizing from the noise.
That covers the 12th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 13. Knuth writes, in Exploration 21, Claude realized that the 2D serpentine function WEO I plus 1j, text of I plus j not equiv m1 bold m, text else I j plus 1 q of I, j equals the coordinate pair I plus 1 j, if I plus j is not congruent to m minus 1 modulo m, else the coordinate pair I j plus 1 had nice properties. It looked promising when a uniform choice is made at fiber 0 and a version of the serpentine at all other fibers, if and only if m is odd.
Claude is performing high-level synthesis here. It dives back into its context window, retrieves the 2D serpentine snake pattern from Exploration 3, and formalizes it into a discrete piecewise function, q of I, j.
It essentially says, keep incrementing I until you hit the diagonal boundary, then increment j.
It then fuses this with its new fiber theory. The proposed architecture is stunning. Make the first slice of the torus perfectly uniform and make every subsequent slice execute a variation of the 2D snake.
But the AI deduces a massive constraint here. This interlocking mechanism might only be algebraically possible if the grid size, mm, is an odd number. Parity, the state of being even or odd, is suddenly dictating combinatorial possibility.
And that's a huge revelation.
That covers the 13th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 14. That triggered a bunch of experiments with simulated annealing at scale, but all was for naught.
This represents the brutal reality of computational mathematics. You can formulate an incredibly elegant hypothesis, the uniform fiber plus the serpentine layers, but when Claude scaled the simulated annealing algorithm to test larger grid sizes like m equals 5 or m equals 7, the heuristic failed.
The search space outgrew the cooling schedule of the annealing process.
The needle was lost in the haystack.
That covers the 14th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 15 gives Claude's own self-assessment. The conclusion after exploration 25 was, SA can find solutions, but cannot give a general construction. Need pure math.
I find this to be the most human-sounding sentence generated by the AI in the entire document. Need pure math.
It's so direct.
Claude recognizes the fundamental epistemological limitation of heuristic algorithms. Simulated annealing is a stochastic optimization process. It can find an artifact, a singular solution to a specific grid size, but it cannot give you the underlying algebraic generator. It cannot provide a theorem.
So to solve Don Knuth's generalized decomposition problem, you need pure, rigorous mathematical logic that transcends specific integer inputs.
Yes, the AI voluntarily abandons its computationally expensive brute force engines and returns to abstract deductive reasoning.
That covers the 15th paragraph. Have you missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 16. So now Claude put on a new thinking cap. At one point it said to itself, maybe the right framing is, don't think in fibers, think directly about what makes a Hamiltonian cycle.
In optimization theory, this is known as escaping a local maximum of thought. The fiber framework was a brilliant dimensional reduction, but it became an ontological trap.
Claude was trying to force the uniform fibers to be the solution.
Exactly, rather than using them as a tool to find the solution. By resetting its framing to the foundational definition of a Hamiltonian cycle, the AI is demonstrating flexible, lateral thinking, wiping its cognitive slate clean.
That covers the 16th paragraph.
Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence. Paragraph 17. Knuth writes, there was a near miss at exploration number 27. Take the 3D serpentine for cycle 0, apply cyclic coordinate rotation to get cycles 1 and 2. The cycle 1 rotation, d$ijk, d0jki plus 1, b mod 3, 3, d sub 1 of ijk equals the quantity d sub naught of jki plus 1 modulo 3. The cycle 2 rotation, $2ijk, d0kij plus 2, b mod 3, 3, d sub 2 of ijk equals the quantity d sub naught of kij plus 2 modulo 3. All three are individually Hamiltonian for every mol 3, 3. 9 tested. Only 3 emelons out of the total vertices, membo-urk-ub vertices, have conflicts. All lie on the hyperplane. Conflict hyperplane I plus j plus k m y to my dan plus I plus j plus k equals m minus 1 modulo m.
The elegance of this near miss is heartbreaking.
It truly is. Claude proposes a master geometric blueprint based on pure rotational symmetry. It takes a massive 3D serpentine paths from cycle 0, and instead of generating new paths, it just algebraically rotates the coordinate axis.
If cycle 0's function is d sub naught, cycle 1 is just d sub naught shifted to the right, and cycle 2 is d sub naught shifted to the left. It generated perfect individual Hamiltonian loops for grids up to m equals 9.
But remember the constraint of decomposition. The 3 cycles must never attempt to use the same directed edge at the same vertex.
Right. Claude maps the collisions and finds that out of thousands of vertices, traffic jams only occur at precisely 3 times the quantity m minus 1 specific points. And remarkably, all those collisions lie on a single 2D slice of the torus, the hyperplane where the coordinates sum to m minus 1.
The symmetry is almost perfect, save for one microscopic structural fault line.
Exactly.
That covers the 17th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 18. Unfortunately, those conflicts couldn't be resolved. Exploration 29 proved that many plausible scenarios were, in fact, impossible. This kills the single hyperplane plus rotation approach entirely. We must allow the direction function to use different values across a rotation orbit.
Claude attempts to patch the faults on the collision hyperplane, but the topological constraints of the Hamiltonian loop forbid it. Fixing a collision on one vertex invariably breaks the unbroken chain of the cycle somewhere else.
So it writes mathematical proofs to itself in Exploration 29.
Demonstrating that the rigid rotational symmetry is fundamentally incompatible with the lack of collisions. It deduces that the ultimate solution must be asymmetrical across its rotation orbit. It kills its own most elegant hypothesis through rigorous deduction.
That covers the 18th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 19. But Aha. Exploration 30 went back to the solution found by SA in Exploration 20 and noticed that the choice at each fiber depends on only a single coordinate. SA seals only on J, S1 and S fuels 2 only on I. This led to a concrete construction, Exploration 31, in the form of a Python program, which produced valid results for M, 3, 5, 7, 9, and 11. Hooray! All three cycles are Hamiltonian, all arcs are used, perfect decomposition.
This is the culmination of everything. Claude abandons the failed geometric symmetry and performs a forensic analysis on the noisy, messy artifact it generated back in Exploration 20 using simulated annealing.
It looks past the noise.
And identifies a profound structural simplicity. The routing decision doesn't require checking the complex interplay of all three coordinates. It depends strictly on the layer S and a single coordinate check.
On the first slice, where S equals 0, you only interrogate the value of J. If you're on the second or third slice, you only interrogate I.
It condenses a mind-bending three-torus constraint problem into a localized boundary check. It writes the Python construction, executes it, and it flawlessly decomposes every odd grid up to M equals 11. The graph is broken open.
That covers the 19th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
We are now at paragraph 20, which introduces the code. Knuth writes, "Here is a simplification of that Python program, converted into C form." And he provides a block of code. Under our unabridged protocol, I'm going to read the logical structure of this C program.
Please do.
He declares variables C, I, J, K, M, S, T, and a character pointer D. It loops through the three cycles C equals 0 to 2. Inside, it calculates the layer, the modular layer assignment, 0 is Ni plus J plus K, B mods M do S equals the quantity I plus J plus K modulo M. Then the core logic. If S is 0, D becomes 0, 1, 2. If J is M1, otherwise 210. Else if S is M1, D becomes 210. If I is 0, otherwise 120. Else D becomes 201. If I is M1, otherwise 102. Then a switch statement based on D at index C. Case 0 increments I mod M. Case 1 increments J mod M. Case 2 increments K mod M.
This tiny block of logic is the artifact of the AI's triumph. We must unpack how this code functions conceptually. The string D, like 0, 210, or 210, is the routing permutation from the symmetric group S sub 3.
The digits 0, 1, and 2 correspond to the spatial directions I, J, K.
The index C represents which of the three cycles we are currently navigating. So the code dictates the following local behavior. Calculate your current layer S. If you are on the ground floor, S equals 0, check your J coordinate. Are you pressed against the maximum boundary where J equals M minus 1? If so, assign the routing template 0, 1, 2. If not, assign 210.
The switch statement then simply executes the instruction for whatever cycle C is active.
It is breathtakingly concise. The AI reduced a 6 to the 27th combinatorial explosion into 3 nested if statements evaluating boundary conditions.
That covers the 20th paragraph and the code block. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Moving to section 4, the rigorous proof for odd M paragraph 21. Philip Stapper has tested Claude's Python program for all odd M between 3 and 101, finding perfect decompositions each time. Thus, he concluded, quite reasonably, that the problem was indeed solved for odd values of M, and he quickly sent me the shocking news.
Stappers behaves as the rigorous engineer verifying the model's output. He strips the AI's underlying logic, translates it into an optimized test script, and hits it with massive compute power.
He tests every odd grid up to 101 by 101 by 101. That is a discrete space of over 1 million vertices.
And the AI's 3 if statements partition the 3 million directed edges flawlessly every single time. In combinatorial mathematics, if a rule holds for a sequence of 50 consecutive odd integer dimensions, the statistical probability of it being a local anomaly collapses to 0. Stappers knows the problem is defeated, prompting the frantic message to Knuth.
That covers the 21st paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 22. Of course, a rigorous proof was still needed, and the construction of such a proof turns out to be quite interesting. Let's look, for example, at the first cycle that is printed. We must prove that it has length. The full cycle length, $303 meal cubed.
This is where Knuth asserts the primacy of human mathematics. Empirical validation via Python script across 1 million vertices is engineering. It is not math.
Right. A formal mathematical proof must logically guarantee, through immutable axioms, that the AI's algorithm will never fail, even as the dimension M approaches infinity.
To prove the decomposition is universally valid, Knuth must demonstrate algebraically that tracing the rules for cycle C equals 0 will step through all the 2 araf. The set of vertices, C103 narrows your cubed points precisely once before returning to the origin.
That covers the 22nd paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 23 sets up the proof rules. Knuth writes, the rule for that cycle is non-trivial, yet fairly simple. The layer sum, do deo plus I plus j plus k, p mod deo boa, s equals the quantity I plus j plus k modulo m. When s equals the quantity I plus j plus minus 1, bump I if I'm in p doa, otherwise bump j. When m in 0, 1, bump k if I 0, otherwise bump j, otherwise bump j. Bump means increase by 1, bump m.
Knuth is taking the AI's abstract C code and crystallizing it into pure mathematical logic specific to the very first cycle. He isolates the conditions. He defines bump mathematically as a quantity x plus 1 modulo m.
So the entire formal proof will hinge on tracking how these specific localized coordinate bumps weave together across the layers to form a structurally sound, non-intersecting global loop.
Exactly.
That covers the 23rd paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 24 provides the trace for the smallest grid. Knuth writes, hence, in the special case m equals 3, that cycle is. And he lists the full sequence. Under our protocol, we're going to trace this. Let's follow the first few steps closely so you, the listener, can visualize the math. The sequence begins at 0, 2, 2.
Stop right there. Let's apply the rule. At coordinate 0, 2, 2, the sum s is 0 plus 2 plus 2 equals 4. Modulo 3, that gives s equals 1. We are on layer 1.
Look at the rules Knuth just defined for layer 1. Bump k if I equals m minus 1, otherwise bump j. Here I is 0, which is not m minus 1, which is 2. Therefore, we bump j.
J goes from 2 to 3, but modulo 3, it wraps around to 0. So the next coordinate must be 0, 0, 2.
And Knuth writes, to 0, 0, 2. Next, we have 0, 0, 2. S is now 0 plus 2 equals 2. Modulo 3, s equals 2, which is m minus 1. The rule for s equals m minus 1. Bump k if I equals 0, otherwise bump j. Here is indeed 0, so we bump k.
K goes from 2, wraps around to 0, so the next coordinate is 0, 0.
And a 0, 0, 0, 0, 0, 0. The rule for s equals 0, 0. Bump I if j equals m minus 1, otherwise bump k. J is 0, not 2, so we bump k. The next coordinate is 0, 0, 1. You can see the deterministic rigor. The cycle weaves through the space layer by layer, driven entirely by these local boundary checks.
By explicitly writing out the full path for m equals 3, Knuth is grounding the reader. Before launching into the abstract algebraic proof with arbitrary variables, he forces you to physically verify the local integrity of the AI's structural ribbon.
That covered the 24th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 25 is the trace for m equals 5. Knuth writes, and in the special case m equals 5, it's Knuth, and provides an entire block of 125 coordinates. I will read a segment to demonstrate the density. 042 to 002 to 01212 to 022 to 022 to 023 to 034 to 04 to 000 to 001 to 01 to 012 to 013. It systematically winds through the space until it returns to 042.
The visual block of text in the paper is deliberately overwhelming. Knuth includes all 125 steps for m equals 5 to demonstrate the geometric complexity of the cycle.
Tracking this pattern by hand across 125 steps is dizzying for a human brain.
Right, yet the AI's 3 localized if statements generate it flawlessly without ever causing a collision. It visually proves that local simplicity can generate immense global complexity.
That covers the 25th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 26 begins the logical deduction. Knuth writes, triples for the same value of s are spaced exactly m steps apart. To prove that all the full set of vertices, m tilde 3 dollars creeds, we need to prove that the layer vertex count, tilde 2 meter squared, triples for any given value of s are all present.
Here begins the grand architecture of Knuth's formal proof. He utilizes a profound mathematical shortcut. He observes the heartbeat of the algorithm. Because every single step increments the total coordinate sum s by 1, it takes exactly m steps to cycle through all the layers and return to the layer you started on. The vertical movement is perfectly rigid.
Because of this rigid repeating rhythm, Knuth states we do not need to prove the cycle hits all m-cubed points directly.
If we can simply prove that the cycle hits every single one of the layer vertex count, 2n2-seater me-squared coordinates located on just one specific slice, say, the ground floor where s equals 0, then the vertical rhythm mathematically guarantees it must have swept through all the other layers properly as well. He collapses the burden of the proof by an entire dimension.
That covers the 26th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 27. Notice that the first coordinate, I, changes only when s key 0 and j equals 1. Thus, the layer vertex count, 2 nearest squared, triples with any given value of the first coordinate I all occur consecutively. Our example cycles indicate this by starting at the vertex where I is just changed to 0 instead of starting at vertex 0, 0.
Knuth is observing the internal gearing of the AI's algorithm. Think of an analog odometer in a car. The rightmost dial, K, spins the fastest, the middle dial, J, spins slower, and the leftmost dial, I, spins the slowest.
Knuth isolates the I coordinate and proves it acts as the slowest dial. Look at the rules. I is almost never allowed to bump.
It only increments under extremely restrictive conditions. You must be exactly on the first slice, S equals 0. A and D, your J coordinate, must be fully maxed out at the edge, M minus 1. Because this boundary condition is so rare, the cycle is forced to exhaustively explore every permutation of J and K on that level before the lock opens and I clicks up by 1. This odometer behavior is the mechanical core of why the loop fills the entire space.
That covers the 27th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 28. Notice that the cycle elements with I equals 0 must start in general with the vertex. The generic starting vertex, $0, Basker's 1, 2, 2, 0, M minus 1, 2, because the previous vertex must have had I, J, M1, and S equals 0.
Yeah.
And the generic starting vertex, 0, people 1, tan 2, 2, 0, M minus 1, 2, which has S1, is followed in general by 0, 0, 2, 0, 1, 2. The penultimate general vertex, 0, minus 3, 2, 0, M minus 3, 2, 0. The final general vertex, 0, betas 3, 3, 0, minus 3, 3, taking us back to S equals 0.
Knuth moves from concrete numbers to general algebraic tracking. He traces the exact sequence of coordinates, starting from the moment the I dial clicks to 0. He maps the path conceptually through the layers, advancing J and then advancing K, mathematically proving that the sequence perfectly loops back down to the ground layer, S equals 0.
He is verifying that the localized steps form a continuous, predictable mathematical ribbon.
Exactly.
That covers the 28th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 29. In general, the sequence tracker, 0 meters K, 0, M minus K, K is immediately followed by the incremented sequence tracker, 0 meter K, K plus 1, 0, M minus K, K plus 1, when the inequality bound on K, 1 kilometer, 1 is less than K, which is less than M, and then J increases until we reach the subsequent target vertex, 0 meter K plus 1, 0, M minus K minus 2, K plus 1, whose successor is the final target vertex, 0 meters K, K plus 2, 0, M minus K minus 2, K plus 1. Thus, K is increased by 2 modulo M each time we hit a vertex with S equals 0. Since M is odd, we'll eventually get to the destination vertex, 0, 1, 0, and 0, 1, 0, M minus 1, one at which time we will have seen all the layer vertex count, M dollar 2 meter squared vertices of the form 0, JK, and the successor of the destination vertex, 0, 1, or 1, 0, M minus 1, 1 is the next I vertex, 1 dollar 1 over 1, M minus 1, 1. This is the absolute crux of the entire paper. This is the mathematical revelation of why Claude's solution works, and crucially, why parity dictates the universe. Knuth tracks the variables through a full vertical loop and proves that every single time the path returns to the base layer, S equals 0, the K coordinate has shifted by exactly 2.
Now, think deeply about modular arithmetic. If you have an even modulo, say 6, and you take steps of 2, you traverse 0, 2, 4, and then you wrap right back to 0. You short circuit, you completely miss the odd coordinates.
But if your modulo is an ODD number, say 5, and you take steps of 2, you traverse 0, 2, 4, 1, 3, and then 0.
Because 2 and any odd number are coprime, stepping by 2 guarantees you will sweep through every single integer in the set before repeating. Knuth proves that because the AI's internal rhythm shifts K by 2, the grid dimension M must be odd to prevent a short circuit. The AI stumbled upon this parity constraint heuristically during simulated annealing, but Knuth has now algebraically proven the necessity of the odd number.
That covers the 29th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 30. So far, so good. In general, the cycle elements whose component I satisfies, the middle downs for I are MS1, 0 is less than I, which is less than M minus 1. We'll start with the general I starting vertex, IM1, 2 I, M minus 1, 2 minus I, where the modulo term 2 minus I is, of course, evaluated mod M. If all goes well, those elements should include all the layer vertex count, mesa squared vertices that begin with I, ending with the general I ending vertex, I, m minus I, m minus 1, minus I, whose successor is the incremented I vertex, I plus 1, ms1, minus 1, I, m minus 1, minus I, and autos go well. We repeatedly advance the second component, except when s as I plus 1, m minus 3, more I, m next 3, 3I, as as I, m 3, I, m, I, m, I, m, I, m, minus 2, minus I, m minus 3, 3 minus I, and so on up to I0, m minus 1, 1 is I.
Having rigorously proven the behavior when I equals 0, Knuth generalizes the proof via induction for all middle values of I in the space. He uses algebraic substitution to demonstrate that the shift by 2 coprime logic holds regardless of the specific layer or coordinate.
He proves that the sequence predictably and exhaustively sweeps through every possible combination of j and k on a level before the odometer lock perfectly clicks I up to the next integer.
The phrase, "and all does go well," is Knuth's joyful confirmation that the AI's algorithm remains topologically sound across the entire inner volume of the 3 torus.
That covers the 30th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 31 brings the proof of the first cycle to a close. Finally, we reach the final boundary vertex, M1, M1, 33, minus 1, minus 1, minus 1, 3, the first vertex of which I am U1. The local rules change again. From now on, we'll repeatedly advance the third component except when 1 mu1, the vertices we see when emul are R. The final sequence of S equals 0 vertices, M1, 1, 1, M1 minus 10 dots, M1, M1 minus 1, 0, 1, M minus 1, 1, 0, and so on, up to M minus 1, M minus 1, 2, QED.
The final boundary condition. Knuth proves the algorithmic behavior at the absolute edge of the 3D space, where the I dial reaches its maximum value of M minus 1.
He mathematically demonstrates that the AI's specific rule changes for this extreme boundary condition cleanly and perfectly wrap the terminal end of the Hamiltonian line right back to the original starting coordinate, snapping the lock closed.
The letters QED quod erat demonstrandum, meaning what was to be demonstrated, signal absolute mathematical victory. Knuth has translated an AI's heuristically derived C code into an unshakable algebraic theorem.
That covers the 31st paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 32. We've now proved that the first cycle, the cycle for C equals EOU in the C program, is Hamiltonian. Similar proofs can be carried out for the other two cycles. See the appendix.
This is standard practice in advanced mathematical literature. Once the foundational logic and structural rhythm are proven for the most complex case, variations that follow the exact same affine geometry don't need to be explicitly spelled out in the main text.
Knuth relegates the proofs for cycle 1 and cycle 2 to the appendix, mathematically certain that the underlying coprime architecture holds. The generalized decomposition, splitting the graph into 3 separate valid paths, is officially solved for all odd dimensions. That covers the 32nd paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Moving to section 5. Generalization and Claude-like decompositions. Paragraph 33. For fun, let's consider a larger class of cycles for which such proofs exist. Indeed, it turns out that there are hundreds of ways to solve the stated decomposition problem for odd bound. Claude Opus 4.6 happened to discover just one of them by deducing where to look.
For fun, he says. This is Knuth flexing. Having vanquished the specific problem posed, he now seeks to map the entire taxonomy of possible mathematical solutions.
He reveals that Claude's specific permutation rule was not the only solution allowed by the universe, but merely one artifact in a larger family of structural truths. Claude found the needle, but Knuth is now going to categorize the haystack. That covers the 33rd paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 34 rigorously defines this taxonomy. We shall say that a Hamiltonian cycle C for angles 3 is generalizable if the following construction yields a Hamiltonian cycle for all odd m. The inequality bound, say 33, is greater than or equal to 3, given an arbitrary vertex ijk for the coordinate bounds, 0 die, j, k, mla. 0 is less than or equal to capital I, capital J, and capital K, which are strictly less than m. Let the projected I coordinate 1 doll, I equals I prime, the projected j coordinate jj equals j prime, the projected s coordinate c s equals s prime, and the projected k coordinate k mod thane mod 33 k equals the quantity s minus I minus j modulo 3, where the map sum I plus j plus k Plato m, capital S equals the quantity capital I plus capital J plus capital K modulo m, the prime mapping 0 0 0 0 prime equals 0, the prime mapping edge m is 0 42, the quantity m minus 1 prime equals 2, and the prime mapping middle $6 0 prime equals 1 for the bounds of x, $0 x limit z to 1, 0 is less than x, which is less than m minus 1. Obtain the successor of ijk by bumping the coordinate that cycle c points when forming the successor of ek.
This is a phenomenal conceptual leap. Knuth is building a mathematical translation engine to test for universal scalability. He is asking, if I have a solution that works on a tiny 3 by 3 by 3 grid, how do I mathematically prove it will work on a 99 by 99 by 99 grid without actually running the computation?
He creates a prime mapping function that compresses any massive coordinate space down to a proxy 3 by 3 by 3 template.
The rules are elegant. If a capital coordinate in the massive grid is at the absolute boundary, 0, map it to 0. If it is at the maximum boundary, m-1, map it to 2. If it is anywhere in the massive middle expanse between 0 and m-1, squash it down to 1.
This essentially categorizes every point in an infinite space into 1 of 3 states: start, middle, or end. If you can use the routing rules of the tiny grid on these squashed proxy coordinates, and it successfully generates a non-intersecting Hamiltonian loop in the massive grid, then the original tiny cycle is deemed mathematically generalizable. That covers the 34th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Paragraph 35 gives a concrete numerical example. For example, if m is 5 and ijk equals 301, we have I equals 1, j equals 0, s equals 4, s equals 2, k equals 1. So the successor of 301 will be either 401 or 311 or 302, depending on whether C contains the arc. The directed arc I, 101 to 201 to 201, or directed arc J, 101 to 111, 1 to 1, or directed arc K, 101 to 1 to 121 to 122.
Knuth is grounding the abstract mapping engine for the reader. He takes a specific coordinate from a larger 5 by 5 by 5 grid, 3, 0, 1. He squashes it through his prime roles. Because 3 is a middle number, it becomes 1. Because 0 is a boundary, it stays 0. He calculates the s and k proxy values. Ultimately, the massive coordinate 301 is proxy to the tiny coordinate 101.
Whatever specific directional choice the small reference graph makes at 101, the big graph is forced to mimic at 301. It is a brilliant way to enforce structural conformity across varying dimensions. That covers the 35th paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The text continues in the next paragraph. Claude's cycle in the example above for m equals 3 is generalizable. Indeed, we've seen its generalization for m equals 5. But it's easy to find cycles that are not generalizable. For instance, if C is the cycle. And then Knuth provides a massive trace of a cycle for m equals 3 that is 27 steps long, noting it happens to be the lexicographically smallest of all Hamiltonian cycles. He then shows its generalization map trace for m equals 5, and he concludes, oops, this cycle has length 75, not 125.
This perfectly illustrates why the property of generalizability is so rare and mathematically demanding. You can easily find a path that works flawlessly on the small 3 by 3 by 3 grid. But when you try to apply its logical blueprint to the 5 by 5 by 5 grid using Knuth's compression engine, the topological structure shatters.
Instead of successfully weaving through all 125 points, the cycle short circuits. It loops back onto its origin after only 75 steps, leaving 50 points entirely untouched.
This proves that most solutions are merely local accidents of small numbers. They possess no underlying universal truth. Claude managed to find a universal truth.
That covers the non-generalizable example paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The next paragraph quantifies this landscape. Knuth writes, it turns out that there are exactly 11,502 Hamiltonian cycles for m equals 3, of which exactly 712 generalize to Hamiltonian cycles for m equals 5. Furthermore, exactly 996 of them generalize to Hamiltonian cycles for both m equals 5 and m equals 7. And those 996 are in fact generalizable to all odd m1.
Knuth relies on his computational mastery here. He exhaustively maps the entire combinatorial universe of the m equals 3 case and determines there are exactly 11,502 distinct ways to trace a valid loop. He then runs all 11,502 through his scalability engine for m equals 5.
Roughly 90% of them shatter and short circuit, leaving only 1,012 survivors.
He pushes those survivors to m equals 7 and a few more break, leaving exactly 996. Knuth then mathematically proves that if a sequence survives up to m equals 7, it possesses the perfect algebraic DNA to scale infinitely to any odd dimension. These 996 are the golden cycles.
That covers the numerical landscape paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The next paragraph defines a new taxonomic term. Now, here's the point. Let's say that a decomposition is Claude-like if it can be generated by a C program like the one above, in which the permutations D of 0, 1, 2 depend only on whether I, J, and S are 0 or me 1 or not, No special cases other than 0 and me1 are allowed to affect the choice of D.
This is a remarkable moment in computer science history. A mathematical structure is officially named after an AI's heuristic architecture. Knuth formally defines a Claude-like solution as one that relies purely on evaluating the extreme boundaries of the grid, checking if coordinates are exactly 0 or exactly m-1.
If an algorithm requires complex condition checks in the middle of the grid, it is disqualified. Knuth recognizes the profound elegance of the AI's boundary condition logic and uses it to categorize an entire specific class of universal algorithms. That covers the definition of Claude-like. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Next, Knuth poses a formal theorem. Theorem. A Claude-like decomposition is valid for all odd M1 if and only if each of the three sequences that it defines for m equals 3 is generalizable. Proof. If those three sequences aren't Hamiltonian, or if they don't generalize to Hamiltonian cycles for all odd M1, they certainly don't define a valid decomposition. Conversely, if they are Hamiltonian cycles that generalize to Hamiltonian cycles for all odd M1, they certainly are valid. Every vertex Ike appears in each of the three cycles, and its three outgoing arcs are partitioned properly because D is a permutation.
This theorem brilliantly bridges computational enumeration and abstract algebra. Knuth proves that you never need to test a proposed Claude-like algorithm on infinitely large grids. You only ever need to test its output on the tiny m equals 3 case. If the three resultant cycles belong to the list of the 996 golden scalable cycles, then the entire decomposition is guaranteed by mathematical law to be valid for all odd infinity. The logic is airtight. Because the D matrix guarantees an S sub 3 permutation at every single point, collisions are impossible. He has reduced an infinite multidimensional search problem into a closed, finite verification check.
That covers the theorem and proof paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Next paragraph. By setting up an exact cover problem using the 11,554 cycles for n lower 3, we can deduce that there are exactly 400,554 solutions to the 353i3 decomposition problem. And in a similar fashion, if we study all ways to cover every arc by using just 3 of the 996 cycles that are generalizable, we find that exactly 760 of those 4,554 solutions involve only generalizable cycles about 1 in every 6. Consequently, the theorem tells us that exactly 760 Claude-like decompositions are valid for all odd in M1.
Let's contextualize the exact cover problem. Remember, the grand objective isn't just to find one cycle. We have to find 3 distinct cycles that interlock to color every single arrow in the entire graph exactly once without overlap. Knuth translates this into an exact cover matrix problem, likely solving it using his famous algorithm X or dancing links technique. He feeds the 11,502 valid m equals 3 paths into the matrix. The algorithm discovers exactly 4,554 ways to perfectly assemble 3 cycles to cover the graph. But Knuth only cares about the universally scalable ones. He restricts the puzzle pieces to strictly the 996 golden cycles. The computation completes. Exactly 760 universal blueprints exist. Out of a combinatorial infinity, there are exactly 760 correct mathematical answers. Claude Opus 4.6 autonomously navigated the dark and found one of them.
That covers the exact cover paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Next paragraph. Maybe the decomposition that Claude found wasn't the nicest of those 760. Can we do better? I looked at several of them and found that they have somewhat different behaviors, yet I didn't encounter any that were actually nicer.
This introduces the concept of mathematical aesthetics. Mathematicians don't just judge proofs on correctness, they judge them on niceness, or elegance, simplicity, symmetry, ease of computation. Knuth, now possessing the complete taxonomy of all 760 correct universal answers, evaluates them to see if the AI stumbled into an overly complex or ugly local solution. His conclusion is a profound compliment to the machine. Claude's algorithmic logic was essentially as computationally elegant as anything the universe allowed.
That covered the nicest paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Next paragraph. The dependence on I, J, and S means that these decompositions don't have cyclic symmetry. I did notice to my surprise that 136 of the 760 generalizable 3-terry-3 cycles remain generalizable when we map Ake to Jakey. However, none are common to all 3 mappings.
Knuth digs deeply into the geometric symmetry of the 760 solutions. Because the AI's rule treats the coordinates I and j differently based strictly on the layer S, the physical shape of the global loop is inherently lopsided. It lacks perfect 3D rotational symmetry. Knuth mathematically rotates the solutions, swapping the definitions of the axes from eq to jq, and checks if the cycles survive the translation. He finds that only a subset, 136 of them, maintain their scalability under a partial rotation. Ultimately, he proves that absolutely no single solution can possess perfect, omnidirectional symmetry. The topological fabric of the graph itself prohibits it. The AI was mathematically forced to adopt an asymmetrical path to survive.
That covers the rotational symmetry paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
We now move to section 6, the AI workflow and the even M frontier. Philip told me that the explorations reported above, though ultimately successful, weren't really smooth. He had to do some restarts when Claude stopped on random errors. Then some of the previous search results were lost. After every 2 or 3 test programs were run, he had to remind Claude again and again that it was supposed to document its progress carefully.
This paragraph brings the soaring abstract mathematics back down to the gritty, frustrating reality of software engineering in 2026. Despite its capacity for brilliant deductive leaps, the AI agent is fundamentally fragile. It drops its context window, it throws random execution errors, it constantly forgets its primary system directive to maintain the plan.md scaffolding file. Stappers had to act as a relentless project manager, constantly corralling the genius-level intellect back onto the operational rails. It highlights that the bleeding edge of AI was not limited by raw intelligence, but by agentic reliability and execution consistency.
That covers the workflow paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The next line. Delicious success for odd M at exploration number 31 came about 1 hour after the session began.
1 hour. Stop and absorb that. An open combinatorics problem bound for Volume 4 of The Art of Computer Programming. A problem that could have taken a postdoctoral human researcher months of intense focus to crack, transitioning constantly between abstract theoretical mapping, Python coding, and SAT solver optimization, was entirely demolished by the human-AI partnership in 60 minutes. The velocity of discovery is terrifying.
That covers the success timeline paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Next paragraph. This decomposition problem remains open for even values of M. The case M edges 2 is proved impossible long ago 1. As part of exploration number 24, Claude said that it had found solutions for M equals 4, M equals 6, and M equals 8, yet it saw no way to generalize those results.
The mountain is only half climbed. The elegant Claude-like rules fundamentally rely on the coprime nature of stepping by 2 around an odd-numbered circle. As Knuth proved earlier, that specific logic shatters completely if the dimension M is an even number, causing massive short circuits. The text references a 1982 paper proving the M equals 2 case is topologically impossible. Claude, leveraging pure heuristic brute force, managed to find localized chaotic solutions for grids of 4, 6, and 8, but it admitted total defeat in finding a universal algebraic theorem to link them. The even numbers remained an impenetrable dark forest.
That covers the even values problem paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Next paragraph. Philip also told me that he asked Claude to continue on the even case after the odd case had been resolved. But there, after a while, it seemed to get stuck. In the end, it was not even able to write and run Explore programs correctly anymore. Very weird. So I stopped the search.
This is a fascinating glimpse into AI cognitive degradation. Pushed against a wall of extreme mathematical complexity where its previous elegant heuristics failed entirely, the model's coherence collapsed. It didn't just fail to deduce the answer, its fundamental ability to execute basic Python code syntax degraded. The immense cognitive load of tracking the massive state space of even-numbered toruses overwhelmed its attention mechanics. Stappers, recognizing the tool had fundamentally broken, halted the experiment.
That covers the AI degradation paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Next paragraph. All in all, however, this was definitely an impressive success story. I think Claude Shannon's spirit is probably proud to know that his name is now being associated with such advances. Hats off to Claude.
A poignant sign-off from Knuth regarding the main text. Claude Shannon is the undisputed father of information theory, the man who mathematically defined entropy in communications and essentially invented the concept of the digital bit. Anthropic explicitly named their AI model Claude in his honor. Knuth, a contemporary to the dawn of computer science, acknowledges that the silicon architecture has finally proven worthy of its namesake's legacy.
That covers the conclusion of the main text. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the appendix and the rapidly escalating postscripts.
Let's rigorously examine the appendix logic. Appendix, Claude's second cycle, C1, is governed by the following rules. If S equals 0, bump J. If the middle layer is bound, $0 bill plus 0 is less than S, which is less than M plus 1, bump. If S 0, 1, and I 0, bump K. If S middle 1 and I equals 0, bump J. Knuth goes on to trace the vertices mathematically, mirroring his proof for cycle 0.
As we noted earlier, Knuth provides the rigorous proof parameters for the second cycle here. The logic is a functional reflection of the first cycle, relying heavily on assessing the layer S to decide which spatial coordinate to increment. It maintains the identical shift by two-orbital coprime architecture that guarantees Hamiltonian coverage.
He does the same for the third cycle. Claude's third cycle, C2, is governed by somewhat more complex rules. If Sx equals 0 and J re 1, bump I. If S0 and J was below 1, bump K. If the middle layer is bound, $0 M1 1, 0 is less than S, which is less than M minus 1, and I know 1, bump K. If the middle layer is bound, $0 Mi1, 0 is less than S, which is less than M minus 1, and I 1, bump share. If S mi 1, bump I. He traces this to prove it strictly follows the modulo shifting logic.
We can clearly see why Knuth relegated this to the appendix. The bump rules for cycle 2 are vastly more granular, requiring more specific dual boundary checks than cycle 0 or 1. But structurally, Knuth's algebra proves it perfectly interlocks with the others to complete the 3-meter cubed edge decomposition without a single overlapping arc.
That covers the appendix. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the postscript.
The document shifts tones wildly here. Real-world events begin moving incredibly fast. Postscript. On March 3, Stappers wrote me as follows. The story has a bit of a sequel. I put Claude Opus 4.6 to work on the M, even cases again for about 4 hours yesterday. It made some progress, but not a full solution. The final program sets up a partial fiber construction similar to the odd case, then runs a search to fix it all up. Claude spent the last part of the process mostly on making the search quicker instead of looking for an actual construction. It was running many programs trying to find solutions using simulated annealing or backtrack. After I suggested to use the OR Tools CPSAT part of Google's open source toolkit with the add circuit constraint to find solutions, progress was better since now solutions could be found within seconds. This program is for.
Notice the timeline. March 3. Stappers refuses to give up. He resets Claude's context and accepts the even numbers again. The AI attempts to force its successful fiber architecture onto the even space, but because even numbers break the coprime shift by 2 logic, the architecture leaves massive disconnected holes in the path. Fascinatingly, Claude then spends hours writing metacode to optimize the brute force search algorithm to patch those holes rather than attempting to deduce a pure math theorem. Stappers intervenes, effectively handing the AI a calculator, prompting it to integrate Google's OR tools, a highly optimized industry-standard constraint programming solver. The AI seamlessly integrates the external tool API, and suddenly it can find localized answers for small even grids in seconds. Human and machine are iterating their software tool use in real time.
That covers the March 3 postscript paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The very next day, a breakthrough arrives from across the globe. Then on March 4, another friend, Hoboon Swan, in Singapore, wrote as follows. I have a code generated by GPT 5.3 codex that generates a decomposition for even M. The inequality bound TEAT8AA is greater than or equal to 8. I've tested it for all even M from 8 to 200 and a bunch of random even values between 400 and 2000, and it looks good. Seems far more chaotic to prove correctness by hand here, though the pattern is way more complex. That program is 5. Wow. The graph for M2000 has a number of vertices, 2033, $8 billion vertices.
The international race is on. Another computer scientist, using a completely different AI model from a competing company, OpenAI's GPT 5.3 Codex, a model fine-tuned entirely on code generation, suddenly cracks the code for the impenetrable even numbers. The model generates a black box algorithmic pattern that mathematically decomposes the graph for massive even numbers. How empirically tests it up to an M equals 2000 dimension grid. Knuth, a man who has seen it all, drops a literal wow in the text because the geometry of an M equals 2000 grid means the AI's algorithm successfully navigated a closed topological space containing the number of vertices, 2,338 billion points without a single intersection error. However, Han notes a profound limitation. The AI's generated code executes flawlessly, but the geometric pattern it produces is incredibly chaotic. Unlike the elegant, human-readable Claude solution, this even solution is practically impossible for a human mathematician to parse and prove by hand. It's an alien artifact.
That covers the March 4 postscript paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
We move to the postscript. Kevin Buzzard just told me that Kim Morrison from the Lean community quickly formalized my proof that Claude's construction is correct. Indeed, Kim had posted his verification online already on March 4/6. That's good to know because I've been getting more error-prone lately.
This represents the emerging third pillar of modern computational mathematics. First, the AI agent generates a heuristic hypothesis. Second, Knuth writes the human-readable algebraic proof. Now third, Kim Morrison translates Knuth's proof into Lean. Lean is a mechanized, automated theorem-proving language based on the calculus of inductive constructions. It systematically checks every single logical deduction down to the absolute foundational axioms of mathematics. It confirms absolutely, without a shadow of human error, that Knuth's reasoning is flawless. Knuth's self-deprecating comment about being error-prone highlights exactly why formalized, machine-checked proofs are rapidly becoming the gold standard in advanced mathematics.
That covers the Lean formalization paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The postscript continues. On another front, Maximilian Reitzauer, aka Exocija, has found a new construction for odd-m that is probably the simplest possible from the standpoint of computation, although it might perhaps not have the simplest proof. We can get a valid decomposition by replacing lines 8-10 of the C program by if S is 0D, 2 is gizmeta 1, 0, 21, else of 0, SL 0, 0, gozi 1, no 2, it's mano, LC 0, 1, 2. Notice that this solution uses only S and J, not I. Furthermore, the identity permutation 0, 1, 2 is used at almost every step.
The open source community begins heavily iterating on the AI's initial discovery. Maximilian Reitzauer examines the bounded space of 760 possible universal solutions Knuth previously mapped out. He finds one specific instance that is computationally vastly simpler than Claude's original algorithm. Reitzauer's solution completely removes the need for the processor to check the I-coordinate entirely. It relies solely on evaluating the layer S and the J-coordinate. Even better, for almost the entirety of the massive inner volume of the grid, it just defaults to the most basic directional instruction possible. 0, 1, 2. Go I, then J, then K. It is an absolute masterstroke of algorithmic cycle optimization.
Knuth adds a note about how Reitzauer found this. I would have found the solution myself if I'd taken time to look carefully at all 760 of the generalizable solutions for MEWOL3, because this one is hashtag 369 on that list. He told me on March 6 that he found his proof 7 by pasting text back and forth between GPT 5.4 extended thinking and Claude 4.6 sonnet thinking.
This is a preview of the paradigm shift in the final paragraphs. Reitzauer didn't isolate this elegant solution through solitary human genius. He acted as a prompt arbiter, pacing concepts back and forth between two different highly advanced AI models, GPT 5.4 and Claude Sonnet, letting their internal logic engines debate, refine, and optimize the math until the absolute optimal theorem emerged.
That covers the Reitzauer paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Then the document hits us with breaking news. Breaking news. The problem for even values of M is no longer in doubt. First, I heard again from Ho Boon Swan, who exercised the newly released GPT 5.4 Pro as follows. Your task is to prove rigorously that the algorithm given in 5 genuinely does always yield 3 cycles of length. The cycle length, $320 cubed each when M is an even number. The inequality bound, 8, is greater than or equal to 8. It would be good to give insight on why this algorithm works, as well as if there are simpler constructions. For context, see https://cs.stanford.edu, Knuth papers claude-cycles.pdf.
The timeline is accelerating exponentially. OpenAI drops a brand new, vastly more capable reasoning model, GPT 5.4 Pro, mid-story. Ho Boon Swan immediately takes the chaotic, alien-looking, even number algorithm generated by the older Codex model, feeds it into GPT 5.4 Pro, provides Knuth's draft paper for context, and commends the AI to do what humans could not: generate the formal, rigorous algebraic proof explaining exactly why the chaotic code functions correctly for infinite even numbers.
That covers the setup for the breaking news paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
Knuth writes the result of that prompt. The result was a beautifully formatted and apparently flawless 14-page paper 8, containing the desired exposition and proof. Ho said this was entirely the machine's doing. He didn't have to edit the paper in any way. And GPT 5.4 Pro's fascinating record of the entire interaction is available on line 9.
Let the magnitude of this event sink in. A machine ingested a highly chaotic, incomprehensible algorithmic construct spanning an 8 billion point geometry, autonomously deduced the underlying algebraic architecture bridging infinite dimensions, and zero-shot generated a 14-page, flawlessly formatted academic mathematical paper rigorously proving it. And it did this nearly instantly, requiring zero human editing or intervention. The AI is no longer functioning just as a calculator or a heuristic search engine. It is now fully functioning as an elite autonomous mathematician, handling both the abstract discovery and the formal academic exposition.
That covers the GPT 5.4 Pro proof paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the next sentence.
The final update. Finally, I heard from Keston Aquino-Michaels, who has brought these studies to a fitting conclusion and recorded them faithfully in 10. Like Reitbauer, he interacted with 2 data-sharing LLM agents that have complementary skills, namely GPT and Claude. The result was yet another valid decomposition for the case of odd M, together with an elegant decomposition for the case of even M that's considerably simpler than 5. Among other things, he turned up a relevant reference 11 that I'd missed, although it doesn't solve the decomposition problem.
Aquino-Michaels synthesizes the entire chaotic methodology of the past week. He establishes a formal multi-agent system workspace. He places GPT and Claude in a shared data environment. By allowing the models to autonomously collaborate, leveraging their complementary architectural strengths, perhaps one specializing in spatial intuition and the other in rigorous logic, checking the swarm intelligence discovers an elegant solution for the even numbers, completely replacing the chaotic one. The AI swarm even acts as a tireless literature librarian, hunting down a highly obscure 2025 mathematics paper that Knuth himself had missed.
Knuth finishes that thought. Best of all, his paper 12 includes a careful analysis of how such joint interaction worked, with potentially significant implications for how new problems can be tackled and resolved in the future.
Knuth recognizes that the combinatorial math problem itself is no longer the main story. The main story is the methodology. The future of theoretical science isn't going to be humans competing against machines. It is going to be humans orchestrating massive, multi-agent, cross-model AI swarms to tackle problems of unimaginable complexity.
That covers the final update paragraph. Have we missed any nuances?
I think we've thoroughly unpacked it. Let's proceed to the final section, the outro.
The outro section is titled Over and Out. Knuth writes, Dear reader, I hope you have enjoyed reading this story at least half as much as I've enjoyed writing it. We are living in very interesting times indeed. But please do not write to me with further thoughts about the topics considered here. Please work with like-minded researchers as much as you can, but without putting me into the loop. I absolutely must get back to writing 3, which will soon contain further stories of a completely different kind, stories that I'm much more qualified to write than stories about LLMs. May the force be with you. And then he lists the references.
It is the absolute perfect sign-off from a living legend. He acknowledges the terrifying historical weight of the moment, very interesting times indeed. But then he firmly, politely closes his door. He is in his late 80s. He has dedicated his entire adult life to completing the art of computer programming. He refuses to let his focus be scattered by the blinding whirlwind of LLM research, playfully telling the world to leave him alone so he can get back to his life's masterwork. He gracefully bows out of the AI revolution he just helped chronicle.
That covers the final paragraph of Knuth's document. Have we missed any nuances?
I think we've thoroughly unpacked the entirety of Claude's cycles, start to finish. We have executed the unabridged protocol perfectly.
We did. But as promised, before we let you go, we want to leave you with one final provocative thought.
Indeed. If you look at the arc of this story, from Claude struggling to hold context while randomly brute-forcing a search space, to GPT 5.4 generating a flawless 14-page rigorous proof without human intervention, just days later it forces a difficult question. If AI agents are now generating the hypotheses, writing the code to test them, discovering the theorems, and writing the final academic proofs, what exactly happens to the definition of a mathematician? Are humans transitioning out of the role of active problem solvers entirely? Are we becoming merely the conductors of an algorithmic orchestra, formulating the scaffolding in the plan.md files, while the machines alone possess the cognitive capacity to compose the actual symphonies of pure logic? It is something to consider as the exponential curve of machine intelligence continues its violent upward bend.
A profound question to end on. Thank you for sitting with us through this exhaustive, unabridged deep dive. Until next time.
Welcome to a highly unique, hyper-focused edition of our deep dive. I am incredibly thrilled you are joining us today because the mission we have laid out is it's a significant departure from our usual format.
Yeah, it really is. Usually our job here is to act as a synthesizer for you. We take a mountain of complex topics, condense them, extract the broad strokes, and just deliver a streamlined overview.
Right. But today we are inverting that process completely. We are looking at a single, relatively short document. But it is a document that represents a seismic, mind-bending moment in the history of computer science, mathematics, and artificial intelligence.
The source material we have in our hands today is a paper titled Claude's Cycles. It was authored by Donald Knuth out of the Stanford Computer Science Department, originally dated February 28, 2026, and revised slightly on March 6, 2026.
And because of the incredible density and the profound historical weight of this specific text, we are implementing what we call the unabridged protocol.
Exactly. And for those listening, the unabridged protocol means we are adopting a strict linear progression through the source material. We will be moving line by line, paragraph by paragraph. We are not skipping over the dense mathematical formulations or the obscure algorithmic tangents.
Every single concept will be unpacked. And crucially, to ensure our logical chain remains pristine, we will be explicitly verifying our comprehension at the end of every major section before we allow ourselves to move forward. We are essentially dissecting this artifact in real time.
We want you to understand exactly why this text demands such extreme granularity and patience. I mean, Donald Knuth is not just an academic observer, he is a foundational pillar of computer science.
Yeah, he is the author of The Art of Computer Programming, it's essentially the sacred text of algorithmic theory. And this paper is his unfiltered, real-time reaction to an artificial intelligence solving an open mathematical problem that he himself was actively trying to crack.
It's really vital to frame why this matters beyond the specific math puzzle involved. This text isn't just about finding paths on a graph. It is a primary source historical log of a massive inflection point.
Right.
It documents the precise window in time when AI transitioned away from merely predicting the next most statistically likely token in a sequence and crossed over into engaging in genuine, creative, automated deduction. It's the anatomy of a machine conducting pure structural mathematics, recorded by one of the greatest human mathematical minds of our era.
Okay, so before we crack open the text and read the opening lines, do we feel we've adequately established the framework of the unabridged protocol and the stakes of the paper? I want to make sure we've hit our first completeness check.
I think the ground rules are solidly set, and the historical context is clear. We're definitely ready to tackle the first paragraph.
Let's dive right into Knuth's opening words then. He begins with a real jolt. He writes, "Shock, shock. I learned yesterday that an open problem I'd been working on for several weeks had just been solved by Claude Opus 4.6 Anthropic's hybrid reasoning model that had been released 3 weeks earlier."
Oh, wow.
Yeah, and he follows that up by stating, "It seems that I'll have to revise my opinions about generative AI one of these days."
The rhetorical weight of those first two words just cannot be overstated. Shock, shock. This is Donald Knuth we're talking about. He has lived through and architected major portions of the computing revolution. He is a man who deals in rigorous, deterministic proof.
Exactly.
For him to open an academic note with a visceral, emotional exclamation signals a profound shattering of expectations. He specifically identifies the model as Claude Opus 4.6 and calls it a hybrid reasoning model. That categorization is critical.
Why is that so critical for the listener to understand?
Because it tells us we aren't just looking at a standard neural network hallucinating text. We are looking at a system that integrates symbolic logic and structural reasoning with natural language processing.
Right. And his admission about revising his opinions it's a massive concession. Knuth, representing the old guard of formal mathematics, was historically very skeptical of generative AI.
Understandably so.
Yeah, the prevailing thought was that these models were sloppy, stochastic parrots, fundamentally incapable of the rigid formalism required for pure math. But look at his immediate pivot to joy in the next sentence.
What does he write?
He writes, "What a joy it is to learn not only that my conjecture has a nice solution, but also to celebrate this dramatic advance in automatic deduction and creative problem solving." I'll try to tell the story briefly in this note. There's zero defensiveness here. He is celebrating the obsolescence of his own skepticism.
The pairing of the terms automatic deduction and creative problem solving forms the thematic core of everything we're about to discuss today. Deduction is the mechanical process of deriving specific truths from general axioms.
Right, the mechanical part.
But creativity, particularly in higher mathematics, is the intuition required to know which axioms to apply and in what novel combination when the path forward is completely obscured. Knuth is explicitly acknowledging that this hybrid model demonstrated both the mechanical rigor and the intuitive leap.
Okay, that covers our deconstruction of Knuth's opening reaction and his shift in perspective on generative models. I'll initiate another completeness check. Are we solid on the emotional and historical starting point of this document?
The magnitude of Knuth's surprise is fully contextualized, yes. I think we can move on to the actual mathematical architecture he was wrestling with.
Knuth immediately gets down to business in the next paragraph. He writes, here's the problem, which came up while I was writing about directed Hamiltonian cycles for a future volume of The Art of Computer Programming.
Okay, let's pause here and dig into the foundations. Since our audience is well versed in the fundamentals of computer science, we don't need to define a basic graph or a depth-first search. We know we are dealing with directed Hamiltonian cycles.
Right, finding a path along one-way edges that visits every single vertex exactly once before closing the loop.
Exactly. But we really need to unpack the specific topological space Knuth is building here because it is brutally constrained. It is a phenomenal combinatorial trap.
How so?
Well, the general problem of finding a Hamiltonian cycle is already computationally intractable for large data sets. It's notoriously difficult because as the number of nodes increases, the possible paths explode exponentially. But Knuth isn't just looking for a path on a random assortment of nodes. He defines a highly structured, hyperspecific three-dimensional manifold.
I'm going to apply our strict formatting protocol right now to convey the math exactly as Knuth wrote it to ensure we lose absolutely nothing in translation.
Please do.
He defines this space as having the vertices defined as 333L's cubed vertices, conk I, jk, co $4, $0, e day, ki, 0, is less than or equal to I, j, k, which are strictly less than m.
Visualizing this is really key for you listening. If our parameter m is 3, we are looking at 27 vertices arranged in a 3 by 3 by 3 grid. Each vertex is defined by its coordinates.
Like an XYZ coordinate system.
Yes. But because the values must be strictly less than m, the coordinates for a 3 by 3 grid are limited to 0, 1, and 2.
Then he defines the edges, or the arcs, and this is where the claustrophobia really sets in. The graph has 3 arcs, from each vertex to the coordinates y bosi plus jk, I plus jk, tt plus ki, jk plus k, jtp plus jk plus, where the modulo arithmetic operation is 1 plus I plus 1. Beam at m I plus is equal to the quantity I plus 1 modulo m.
This modular arithmetic is the secret weapon of the problem. It turns a simple 3D grid into a wraparound toroidal space.
A toroidal space, you mean like a donut?
Exactly like a donut. From any point, you only have 3 legal moves. You can increment your first coordinate, your second, or your third. That's it. But if you are at the edge of the grid, say, your coordinate is m minus 1, incrementing, it doesn't push you off the board, it wraps you all the way back to 0.
Ah, like walking off the right side of the screen in Pac-Man and appearing on the left side?
That is the perfect analogy. You are trapped in a perfectly closed loop of choices. There are no boundaries, no corners to get stuck in, just an infinite looping grid.
And the goal isn't just to find one single Hamiltonian cycle in this space. Knuth states the challenge very clearly. Try to find a general decomposition of the arcs into 3 directed M3 cycles for all m to 2.
This is the real killer of the problem. Since every vertex has exactly 3 outgoing edges and 3 incoming edges, the entire graph is perfectly balanced. Knuth wants to partition the entire graph.
He wants to take all the edges and sort them into 3 distinct, non-overlapping groups. Let's call them the red path, the blue path, and the green path.
Right. And the red path must form a perfect Hamiltonian cycle. The blue path must form a perfect Hamiltonian cycle. And the green path must form a perfect Hamiltonian cycle.
Every single edge must be used exactly once across the whole graph, and every vertex must be visited by each of the 3 cycles.
It requires a level of architectural precision that borders on the miraculous, especially since he wants a general rule for any size grid where BORC is greater than 2. It's not just solving it for a 3 by 3 by 3 grid, it's finding the master blueprint that works for a 1,000,000 by 1,000,000 by 1,000,000 grid.
We've laid out the board. We have the vertices, the modulo wrapping rules for the arcs, and the requirement for a perfect 3-cycle decomposition. I'll run another completeness check here. Does this complete our picture of the foundational problem setup?
The topological constraints and the ultimate objective are perfectly clear. We are ready to look at how humans were faring with this puzzle before the AI stepped into the arena.
Knuth gives us the historical context in the very next section. He writes, I had solved the problem for M equals 3 and asked for a generalization as part of the answer to an exercise in 3. He's referring to his own book drafts there.
Right.
My friend Philip Stappers rose to the challenge and empirically discovered solutions for $4, $16. Therefore, it became highly likely that the desired decompositions do exist, except when M equals 2.
We have to take a moment to differentiate between an empirical discovery and a mathematical proof here. Knuth used sheer human intuition to crack the 3 by 3 case. But Philip Stappers built a search algorithm. He threw raw compute power at the problem and managed to find valid decompositions for grids up to 16 by 16 by 16.
But a 16 by 16 by 16 grid is, 16 cubed. That is over 4,000 vertices.
Yes, 4,096 to be exact. That is a massive search space. Stappers proved that the cycles physically exist in those specific instances.
Why does Knuth say this makes it highly likely that general decompositions exist, rather than just saying it's proven? I mean, 16 consecutive successes seems like a solid track record.
Because finding a solution for m equals 16 tells you absolutely nothing, mathematically speaking, about m equals 17. However, from a heuristic standpoint, if a deeply complex constraint problem yields solutions for 13 consecutive grid sizes, it strongly implies there is a hidden structural rhythm at play. It implies the solutions aren't just random, chaotic artifacts of the small numbers, but that a universal generating rule exists. The problem is, Stappers couldn't find the rule. He could only find the resulting artifacts.
Which brings us to the introduction of the machine into the story. Knuth writes, "Indeed, it was Philip who had the gumption to pose this question to Claude, using exactly the wording above. But Philip didn't just dump the problem into a chat box. He built a scaffolding.
This is a crucial detail.
He also gave guidance coaching, instructing Claude to summarize its ongoing progress. And Knuth provides the exact prompt Phil used. After every explore.xx.p run, immediately update this file plan.md before doing anything else. No exceptions. Do not start the next exploration until the previous one is documented here."
This is a phenomenal piece of insight into advanced prompt engineering. Let's really dig into why Stappers did this. Stappers understands the fundamental architectural limitations of large language models. The context window is volatile.
Right, the context window being the amount of text the AI can remember at any given moment.
Exactly. Over a long reasoning session involving writing, running, and debugging Python scripts, an AI will suffer from context degradation. The attention mechanism of the model starts to lose focus on early instructions. It will forget why a script failed 10 steps ago and start repeating its own mistakes.
It's a brilliant constraint. By forcing the AI to update a markdown file to physically write out its hypothesis, the result of the script, and the plan for the next script, Stappers, is artificially hardwiring a persistent memory state.
He's giving it an external hard drive.
Yes, he is enforcing the scientific method onto a probabilistic text generator. The AI has to look at its own plan.md file and say, exploration 4 failed because of a structural rigidity issue, therefore exploration 5 must avoid that paradigm.
It creates a deterministic chain of thought. Left alone, the model might just generate infinite, slight variations of a broken script until it hits a token limit. This single bolded instruction forces the AI to step out of the execution loop, enter a metacognitive evaluation state, record its findings, and only then return to execution. It's what transforms Claude from a coding assistant into an autonomous researcher.
So we have the human baseline set by Stappers, the realization that an underlying rule likely exists, and the specific prompt architecture designed to force the AI into a structured research loop. Let's do a completeness check. Are we fully aligned on the setup before we look at the AI's first moves?
The environment is perfectly calibrated. We thoroughly understand the constraints the AI is operating under. Let's dig into the actual exploration logs.
Let's follow Claude's initial thought process. Knuth documents the first attempt. And Claude's plan of attack was quite admirable. First, it reformulated the problem. Need sigma. Z3 meter O, S3 betas, finding a permutation of 0, 1, 2 at each vertex. Cycle C at vertex V goes in direction sigma, VCVC. Each resulting functional digraph must be a single Hamiltonian cycle.
Claude's first instinct is elegant. It immediately translates Knuth's graph theory problem into formal algebra.
Let's unpack the algebra for the listener.
Sure. The algebraic space mathbbz M33Z sub m cubed represents our 3D wraparound grid. And 3 to 3, 3 Leah sub 3 is the symmetric group on 3 elements, which simply refers to all the possible ways you can order our 3 choices, bump the first, second, or third coordinate.
So Claude realizes that it doesn't need to physically trace lines through the space, it just needs to assign a specific permutation rule to every single vertex. If every vertex has the correct rule dictating which color gets which exit, the three Hamiltonian cycles will naturally assemble themselves.
Exactly. Having framed the algebra, Claude looks for a silver bullet. Knuth quotes the log from Exploration 1. If sigma is cyclic, then we only need one function g, tested linear g, ai plus bj plus cpk, mod 3, and quadratic variance. No linear or simple quadratic g works.
This is a highly human approach, wouldn't you say? You don't start by assuming chaos. You assume beauty.
You always hope for the elegant equation first. Claude hopes there is a simple mathematical function, maybe just adding the coordinates together and multiplying them by a constant, that will tell it exactly which permutation to use. It tests linear functions, it tests quadratic functions, and it quickly proves to itself that the topological knot they are trying to untie is far too dense for a simple algebraic formula.
So, denied a simple formula, Claude pivots to brute force in Exploration 2. Attempted brute force DFS over sigma assignments for M627 search space. Too slow without good pruning.
This is the harsh reality check. The AI realizes it has to assign one of 6 possible permutations to each of the 27 vertices in the absolute smallest version of the problem.
Wait, where does this 6 come from?
The symmetric group, 3 has $300. There are exactly 6 ways to order 3 items. 1, 2, 3, 1, 3, 2, 2, 1, 3, and so on. So 6 choices raised to the power of 27 vertices gives us a 627/6 to the power of 27 search space.
That is a staggering number.
It's a number so large, roughly 10 sextillion, that a standard depth-first search will run until the heat death of the universe without finding the right combination, unless it has a way to aggressively prune dead-end branches. It recognizes immediately that line searching is computationally doomed.
This forces Claude to look for actual structural properties.
Right.
Exploration 3 is where things get really interesting. Thirdly, it tried what it called 2D serpentine analysis. Key 2D result. The pattern 0 mm chig gives a Hamiltonian cycle in K, Z2 meter per ME1 for M equals 3. Its complement also works, giving a valid 2D decomposition.
And Knuth is visibly impressed by this. He notes in the paper, this is really impressive. First, Claude recognized the digraph as a so-called Cayley digraph with 2 generators, traditionally called E0 and E1.
Let's take a digression here. What is a Cayley digraph and why does it matter?
The AI is abstracting the problem to understand it better. To understand the 3D space, it drops down to 2D. But it doesn't just see a flat grid, it identifies the structure as a Cayley digraph. A Cayley graph is a visual representation of a mathematical group where the edges represent the generators or the fundamental operations of that group.
Okay, so in this 2D slice, what are the generators?
They are simply increment the first coordinate, that's $e sub 0, and increment the second coordinate, that's $e sub 1. By viewing it through the rigorous lens of group theory, Claude finds a repeating serpentine pattern that weaves perfectly through the 2D plane.
Claude takes this 2D insight and attempts to extrapolate it back to 3D in Exploration 4. It outputs a symbolic string for a 3D serpentine pattern. Knuth notes a typographic error in Claude's output, a missing bracket, but he instantly recognizes what the AI was attempting. He writes, it's a classical sequence called the modular gray code.
A gray code is a brilliant construct in computer science. If you are trying to visit every point in a discrete space, a gray code is a sequence where only one single dimension changes at a time between steps. It's the most efficient, least disruptive way to walk through a mathematical grid.
So Claude independently reinvented a foundational combinatorial concept in its attempt to build the first of the 3 cycles.
Yes. But here's the tragedy of it. It builds the cycle, but then it hits a wall. Knuth writes, after deleting this cycle from the graph, Claude looked at the remaining 2 regular digraph and found that it has rigid structure making decomposition difficult. Exploration 5 tries to salvage it, but fails entirely.
Why does it fail if the gray code is so perfect?
This is the classic trap of the greedy algorithm. Claude built one incredibly beautiful, perfect Hamiltonian cycle using the gray code. But remember, the goal is a decomposition into 3 cycles. By perfectly laying down the first track, it consumed a set of edges that left the remaining graph totally fractured.
Ah, so taking the best path first ruined the chances for the second and third paths.
Precisely. The leftover structure was too rigid, meaning there weren't enough degrees of freedom left to weave the second and third cycles. The AI learned the hard way that local perfection can cause global failure.
We've tracked the AI through its algebraic reformulation, the realization that 6 to the power of 27 is too large for brute force, the group theory abstraction in 2D, and the greedy algorithm failure of the 3D gray code. Time for a completeness check. Are we clear on the progression of these first 5 explorations?
The initial strategies, and exactly why they failed mathematically, have been thoroughly dissected. We are ready to move to the major structural breakthrough.
Knuth writes simply, back to the drawing board. The AI spends the next several explorations thrashing. It tries analyzing the choices on specific mathematical planes, hyperplanes where the coordinates sum to m-1. It yields nothing. But then we hit exploration 15.
This is the turning point.
Knuth quotes the log. Nothing promising showed up until exploration number 15, which introduced what Claude called a fiber decomposition. The quotient map S, I plus J plus K, mod M, maps all arcs from fiber Fs to Fs plus 1. The digraph is layered in fiber coordinates, I, J with K equals F plus 1. This is the conceptual leap that makes the entire solution possible. We need to visualize this fiber decomposition for the audience. The AI is looking at this twisted toroidal 3D grid, and it realizes that the chaos is just an illusion. It introduces a new variable, S, which is simply the sum of the three coordinates modulo m. And the mathematical expression here is critical. The creation map equation is AI plus J plus K in Bold-Demote equal the quantity I plus J plus K modulo m.
Let's explore why that equation changes everything. Because of how the rules of the graph work, every time you take an edge, you are adding exactly 1 to exactly 1 coordinate. Your total sum is much increased by exactly 1.
Right. If I'm at 1, 1, 1, my sum is 3. If I take any valid move, I might end up at 2, 1, 1. My new sum is 4.
Exactly. This means you can never move laterally within the same sum. Every single edge in the entire space always points from a vertex with some s to a vertex with some s plus 1.
The graph is instantly transformed. As Claude notes, the digraph is layered. It isn't a tangled web anymore. It is a perfectly ordered high-rise building.
Exactly like a building. Floor 0 only has stairs leading to floor 1. Floor 1 only has stairs to floor 2. And because of this strict layering, a massive dimensional collapse occurs.
Claude states, in fiber coordinates, ij with k, mod m.
It realizes that if you know which floor you are on the fiber S and you know your horizontal position, the I and J coordinates, you don't even need to search for your depth, the K coordinate. The math dictates exactly what K must be based on S, I, and J. The AI has crushed a complex 3D problem into a series of highly constrained 2D sheets stacked on top of each other.
Armed with this fiber coordinate system, Claude goes back to searching. Exploration 18 implemented the full fiber framework as executable code. Exhaustive backtracking for Anka 3 found a valid decomposition in 0.1s, 1 euro 932 nodes.
The dimensional collapse pays off instantly. Earlier, the search space was 6 to the power of 27. Now, by restricting the search to only valid fiber transitions, an exhaustive backtracking algorithm which systematically builds paths and immediately retreats when a constraint is violated solves the base case in 1/10 of a second, only having to search 11,000 nodes.
But the backtracking still isn't efficient enough as the grid grows. Knuth notes, a similarly uniform fiber was found for m equal 4 by simulated annealing as part of exploration 20. This requires us to unpack simulated annealing within the context of this specific graph problem. Let's take a minute to explain this.
Sure. Simulated annealing is an optimization algorithm that borrows its mechanics directly from thermodynamics. In metallurgy, if you heat a metal, the atoms vibrate violently and break out of suboptimal structures. As you slowly cool it, they settle into a highly ordered, perfect crystalline lattice.
So how does that apply to code?
In our algorithm, if you just try to iteratively improve a path, always taking the move that seems immediately best, you often get stuck in a local optimum. That's a path that looks good, but has a fatal flaw 5 steps down, and you can't fix it without making the path worse first.
So the algorithm injects mathematical heat.
Precisely. The heat is randomness. Early in the search, when the temperature is high, the algorithm is allowed to make terrible choices. It's allowed to accept edge assignments that create collisions. This heat allows the algorithm to bounce out of those local optimum traps.
And then it cools down.
Right. As the search runs, the temperature slowly drops and the algorithm becomes more and more greedy, only accepting moves that fix collisions. By applying this thermodynamic principle to the heavily constrained fiber space, Claude manages to force the chaotic edges of the m equals 4 grid to settle into a valid decomposition.
We've covered the paradigm shift of the fiber decomposition, the dimensional collapse using the quotient map, the speed up of backtracking for m equals 3, and the application of simulated annealing for m equals 4. I'll do a completeness check here. Have we fully mapped out the transition into the fiber framework?
The geometric restructuring of the problem is clear, as is the transition to probabilistic search methods. We can now approach the critical inflection point of the entire process.
Knuth documents Claude trying to combine its previous ideas. In Exploration 21, it tries mixing the 2D serpentine math with the new fiber approach and unleashes simulated annealing at a massive scale. Knuth gives the verdict. But all was for naught. The conclusion after Exploration 25 was, SA can find solutions, but cannot give a general construction. Need pure math.
I want to really linger on the specific phrase for a moment, need pure math. This is a staggering moment of machine metacognition. The AI is fundamentally a statistical engine. It has successfully used empirical probabilistic tools like simulated annealing to find isolated solutions for small grids.
But it pauses.
Yes. It pauses, evaluates its own outputs, and realizes that these empirical solutions are messy. They are chaotic artifacts of random heating and cooling. They do not contain a universal logical blueprint that can be applied to a grid of any size.
The AI recognizes the boundary of its own heuristic toolkit and explicitly declares that it must shift cognitive modes. It has to abandon empirical search and engage in structural deduction.
It's the exact moment the calculator decides it needs to be a theoretician.
Following this pivot, Knuth writes, Claude put on a new thinking cap. At one point it said to itself, maybe the right framing is, don't think in fibers, think directly about what makes a Hamiltonian cycle. There is a near miss in Exploration 27. It tries rotating a serpentine pattern and realizes that the cycles are Hamiltonian individually, but they crash into each other when overlaid.
But look at the insight it gleans from the crash. Knuth quotes, only 3 vertices have conflicts. All lie on the hyperplane I plus j plus k is Manutia 1 mod m.
The precision here is truly remarkable. It builds 3 separate, valid tracks. When it puts them together, they collide, but they don't collide randomly. Claude pinpoints the exact mathematical fault line. Every single collision occurs on one specific diagonal plane through the grid, the hyperplane, where the coordinates sum to m-1.
But rather than infinitely tweaking the rotation to avoid the fault line, Claude does something definitive in Exploration 29. Knuth quotes, this kills the single hyperplane plus rotation approach entirely. We must allow the direction function to use different values across a rotation orbit. Exploration 29 mathematically proved that the approach was a dead end.
Proving a negative is a hallmark of high-level mathematics, right?
Absolutely. The AI didn't just give up because it couldn't find a solution. It formulated a rigorous proof demonstrating that a solution within that specific class of rotations fundamentally cannot exist. It slammed a door shut and locked it, dramatically narrowing the universe of possibilities.
Which leads directly to the breakthrough in Exploration 30. Exploration 30 went back to the solution found by SA in Exploration 20 and noticed that the choice at each fiber depends on only a single coordinate. S equals 0 only on J, S equals 1, and S equals 2 only on I.
This is the synthesis of the empirical and the theoretical. The AI looks back at the messy, random data generated by the simulated annealing runs. It applies pure pattern recognition to the noise and finds a breathtakingly simple signal.
It realizes that to decide which permutation to use, you don't need to look at all 3 of your coordinates.
You don't even need to look at 2. If you are on the ground floor, fiber S equals 0 bix, your entire decision matrix collapses down to just looking at your J coordinate. On the other floors, you only look at your I coordinate. The complex 3D topological routing problem has been deduced down to a 1D rule.
And this deduction immediately yields the final algorithm. Exploration 31 produces a Python script that perfectly decomposes the graph for m equals 3, 5, 7, 9, and 11. Claude declares victory in its log. All 3 cycles are Hamiltonian, all arcs are used, perfect decomposition.
The machine traversed the entire life cycle of scientific discovery. Think about it. It started with brute force, moved to geometric abstraction, hit a wall, utilized statistical optimization, recognized the limits of statistics, proved a negative to narrow the search, extracted a 1D signal from chaotic data, and wrote the final universal logic.
We've tracked the AI's metacognitive pivot away from simulated annealing, the mathematical proof of the dead-end hyperplane, the 1D signal extracted from the data, and the final successful script generation. Let's do a completeness check. Does this adequately cover the pure math pivot?
The logical progression from empirical frustration to deductive clarity is fully established. I think let's look at the actual rule set the AI generated.
Knuth takes Claude's Python logic and transcribes it into C code for the paper. Now, we aren't going to read the literal C syntax character by character, but we must understand the spatial logic it represents. The code loops through the 3 cycles using a variable C and assigns a string of directions, a permutation based entirely on the fiber S and a single coordinate.
The architecture of the logic is a simple cascade of conditions. Let's walk through the exact decision tree Claude built, step by step.
The first condition checks the ground floor. If S equals 0, the algorithm only looks for the J coordinate. If J is at its absolute maximum value, the edge of the board, it uses the permutation 0, 20, wealth. For every other position of J on that floor, it reverses it and uses 2 Hanel.
This is incredibly elegant. It means the vast majority of the ground floor acts like a massive conveyor belt pushing everything according to the 210 rule. But there is a single tripwire along the very edge of the grid where J maxes out. Hitting that tripwire flips the permutation, disrupting the flow just enough to weave the cycles together without colliding.
Then the code checks penthouse, the top floor. If S equals m-1, it stops caring about J completely. It now only looks at the I coordinate. If I is exactly 0, the absolute beginning of the grid, it uses 210. For every other position of I, it uses 120.
Again, we see the exact same philosophy. A massive uniform flow dictated by 120 with a single localized tripwire at the I equals 0 boundary that flips the logic.
Finally, the code handles all the middle floors. For any fiber that isn't the top or bottom, it still only checks I. If I is at its maximum, it uses 201. Everywhere else, it uses 102.
When you step back and look at this as a whole, it is staggering. A problem that mathematically exists in a search space of 6 to the power of 27 for the smallest grid, a problem that causes recursive algorithms to choke and die, has been solved by essentially 3 if-then statements based on boundary tripwires. It is a masterpiece of minimalist routing logic.
So we have the spatial breakdown of the C code logic, understanding how it relies on single coordinate tripwires on the top, bottom, and middle fibers to dictate the permutations. Time for completeness check. Are we solid on the mechanics of the generated solution?
The internal logic of the algorithm is perfectly clear. It's time to see how the humans validated this machine-generated logic.
Knuth writes about the immediate aftermath. Philip Spappers tested Claude's Python program for all odd m between 3 and 101, finding perfect decompositions each time. Thus he concluded, quite reasonably, that the problem was indeed solved for odd values of array. And he quickly sent me this shocking news.
Spappers acts like a traditional computer scientist here. He runs the code up to a grid size of 101. For context, a 101 cubed grid contains over 1 million vertices. The AI's simple 3-line logic successfully threads 3 non-intersecting lines through 1 million points without a single error. In the realm of software engineering, generating 50 flawless million-step iterations is definitive empirical proof that the code functions as intended.
However, Knuth represents pure mathematics. He writes, of course, a rigorous proof was still needed, and the construction of such a proof turns out to be quite interesting. Why is generating 1 million perfect vertices not enough? Why does the empirical evidence hold no water for a formal proof?
Because empiricism deals in finite observations, while mathematics deals in infinity. The fact that the algorithm works for m equals 101 offers absolutely zero mathematical guarantee that it won't spontaneously fail due to some hidden harmonic resonance at m equals 103 or m equals 5,000,001.
Right, there could always be an edge case out there.
Exactly. Knuth cannot accept that the algorithm works. He must logically deduce that it is impossible for the algorithm to fail for any generic odd number. He has to prove the underlying structural geometry, not just observe the output.
To do this, Knuth breaks the algorithm down into plain English bumping rules for just the first cycle. He translates the code into a mechanical process. When SME 0 bump I, if nedio mo, otherwise bump K. When 0 me, bump K if I M1, otherwise bump J. When SME bill 1, bump K if I bill 0, otherwise bump J. And he clarifies bump means increase by 1 mod m.
By isolating just the first sequence, Knuth strips away the noise of the permutations. He is just watching a single dot move through the 3D space according to the tripwire rules Claude established.
Knuth then lays out the strategic framework for his proof. Triples for the same value of S are spaced exactly m steps apart. To prove that all m3 triples occur, we need to prove that the m2 triples for any given value of S are all present.
This is where Knuth utilizes the AI's fiber concept to simplify his own human proof. Remember that every step moves you up 1 floor. If there are m floors in the building, it will take exactly m steps to cycle through every floor and return to the ground floor. Therefore, every m step lands on the same fiber.
Oh, I see.
Knuth realizes he doesn't need to prove the 3D path. He just needs to prove that if you stand on the ground floor and log every time the path passes through, it will eventually hit every single possible coordinate on that floor before repeating. If it scrubs the ground floor perfectly, the geometry dictates it will scrub the whole building perfectly.
We've covered the distinction between empirical testing and pure mathematical proof. Knuth's isolation of the bumping rules, and his strategic reduction of the problem back down to the 2D fiber space. I'll do a completeness check. Are we clear on the setup for his formal proof?
The strategic framework is established. Knuth has narrowed the scope of what he needs to prove. Let's look at the mechanical execution of that proof.
Knuth zeroes in on the behavior of the very first coordinate, I. He notice that the first coordinate, I, changes only when s equals 0 and j equals 1. Thus, the M2 triples with any given value of the first coordinate all occur consecutively.
This observation is the linchpin of the whole proof. He looks at Claude's tripwire rules and realizes that I is incredibly stubborn. The algorithm almost never allows I to be bumped. The only way I increases is if the stars perfectly align. You must be on the ground floor, s equals 0, a, and d. Your j-coordinate must be perfectly maxed out at the boundary j equals m-1.
And because that happens so rarely?
Right. Because this happens so rarely, Knuth knows that the path must be spending all its time iterating through every possible combination of j and k while keeping I locked in place.
He traces the path while I is locked at 0. He maps out the loop, tracking how j and k fluctuate as the path climbs up through the fibers and loops back down to the ground floor. He distills the entire loop into a single mathematical consequence. Thus, k is increased by 2, modulo m, each time we hit a vertex with s equals 0.
This is the heartbeat of the algorithm. Every time the path does a full lap of the building and touches the ground floor, the k-coordinate has shifted by exactly 2. It skips every other number. It goes 0, 2, 4, 6.
And this detail is the exact reason why the problem was solved for odd numbers, but left open for even numbers. Knuth writes, since m is odd, we'll eventually get to 0e1, at which time we will have seen all M2 vertices of the form 0jk.
It all comes down to the properties of modular arithmetic. Let's explain this clearly. If you have an even grid, say m equals 4, and you step by 2, your sequence is 0, 2, 0, 2. You are trapped in a subloop, you completely miss 1 and 3, you fail to visit every vertex.
Yeah.
But if your grid is odd, say m equals 5, stepping by 2 forces you to traverse the entire space. 0, 2, 4, 1, 3, 0. Because m is inherently odd, shifting k by 2 guarantees that the path methodically scrubs through every single point on that floor without missing a spot.
Knuth then explains that once the path finishes scrubbing the floor for I equals 0, the tripwire finally triggers I bumps to 1, and the entire scrubbing process repeats perfectly for the new value. He traces this all the way until I equals m-1, ensuring no point is left behind. He concludes the section with the letters QED.
Quod erat demonstrandum, the absolute finality of mathematical logic. Knuth has demonstrated that Claude's localized three-line conditional logic mathematically forces a global, perfectly exhaustive sweep of the entire 3D space, provided the space is odd. The empirical code has been elevated to mathematical truth.
He notes that while he only proved it for the first cycle, similar proofs apply to the other two. We've tracked the static nature of the I-coordinate, the skipping loop that requires odd modular arithmetic, and the final sweeping proof concluding in QED. Time for a completeness check. Does this adequately cover the formal verification of the algorithm?
The logical chain of the proof is fully secure. Knuth has verified the machine. Let's move to how he extrapolates this single discovery into a broader theory.
Now that Knuth has his proof, he acts like an explorer surveying a new continent. He isn't satisfied with just one path. He writes, for fun, let's consider a larger class of cycles for which such proofs exist. Indeed, it turns out that there are hundreds of ways to solve the stated decomposition problem for odd BM. Claude Opus 4.6 happened to discover just one of them by deducing where to look. He introduces the theoretical concept of a generalizable cycle.
This is brilliant structural mapping. Knuth wants to know how many other solutions exist in the universe that follow the same underlying logic as Claude's. He defines a framework to test if a tiny solution, a cycle that just works on the basic 3x3x3 grid, has the mathematical DNA required to stretch and work on infinitely large grids.
He formalizes a translation mechanism.
Yeah.
We shall say that a Hamiltonian cycle C for m equals 3 is generalizable if the following construction yields a Hamiltonian cycle for all odd n up $3. He lays out a complex set of mappings, but the core mechanic is translating the choices made in the tiny grid to the fibers of a larger grid.
He essentially builds a mathematical magnifying glass. You drop a 3x3x3 solution into the lens. The math stretches the local logic of that small cycle across the modulo constraints of a larger grid, like m equals 5. If the stretched logic still forms a perfect, unbroken Hamiltonian cycle, then the original tiny cycle is deemed generalizable. It proves the small cycle contains a universal geometric truth.
But Knuth demonstrates that this isn't a given. He provides a specific example of a Hamiltonian cycle for m equals 3 that fails the test. When run through the translation math for m equals 5, it shatters, creating a short loop of 75 vertices instead of the necessary 125.
This highlights that generalizability is a rare special property. Many solutions for m equals 3 are just mathematical accidents. They only work because the space is so small. As soon as you give them room to breathe in a larger grid, their structural flaws are exposed.
We've covered the theoretical expansion, the definition of generalizability, and the translation framework used to test the structural DNA of small cycles on larger grids. Completeness check. Are we solid on this conceptual expansion?
The framework for analyzing the broader solution space is clear. We can proceed to see what Knuth's data filtering revealed.
Knuth feeds the data through his translation framework. It turns out that there are exactly 1100-702 Hamiltonian cycles for m equals 3, of which exactly 12 generalize to Hamiltonian cycles for m equals 5. Furthermore, exactly 996 of them generalize to Hamiltonian cycles for both n equals 5 and m equals 7. And those 996 are, in fact, generalizable to all odd m1.
This is a beautiful distillation process. Out of roughly 11,500 possible ways to navigate the tiny grid, only about 1,000 have the geometric integrity to expand to m equals 5. And once a cycle proves it can survive expansion to both 5 and 7, Knuth's mathematics guarantee that its DNA is flawless, it will expand infinitely. There are precisely 996 master blueprints.
Knuth then bridges this back to the AI. He defines a Claude-like decomposition. Let's say that a decomposition is Claude-like if it can be generated by a C program like the one above, in which the permutations D of 0, 1, 2 depend only on whether I, J, and S are 0 or 1 or not. He formulates a theorem proving that a Claude-like decomposition is valid universally, if and only if its three component sequences are part of those generalizable blueprints.
He has mathematically defined the exact category of intuition the AI used. Claude didn't invent alien math. It deduced a specific, bounded class of logic rules that rely strictly on checking boundary conditions. Knuth's theorem proves that the AI's logic is formally sound within this space.
Calculating the combinations of these generalizable sequences, Knuth arrives at a final tally. Consequently, the theorem tells us that exactly 760 Claude-like decompositions are valid for all odd M1.
Think about the sheer scale of the search space Claude started in. 6 to the power of 27 for the smallest iteration. Within that near-infinite chaos, there are exactly 760 universal structural solutions that follow this specific boundary logic. Claude Opus 4.6 managed to navigate the noise, deduce the fiber geometry, and extract one of those 760 needles from a multidimensional haystack. And Knuth notes that Claude's solution was as elegant as any of the others he mapped.
We've tracked the statistical filtering from 11,502 cycles down to the 996 master blueprints, the formal definition of a Claude-like decomposition, and the final discovery of exactly 760 universal solutions within that class. Let's do another completeness check. Are we clear on the combinatorial landscape Knuth mapped out?
The exact mathematical context of the AI's discovery within the broader universe of solutions has been thoroughly mapped. Let's move to the reality of the human interaction that generated it.
Before concluding the main body of the paper, Knuth grounds the narrative. Philip told me that the explorations reported above, though ultimately successful, weren't really smooth. He had to do some restarts when Claude stopped on random errors. Then some of the previous search results were lost. After every 2 or 3 test programs were run, he had to remind Claude again and again that it was supposed to document its progress carefully.
This is perhaps the most crucial paragraph for understanding the current state of the art. The paper reads like a clean, deterministic march from exploration 1 to 31. The reality was a friction-filled, messy collaboration.
Yeah, the AI suffered from software crashes, memory degradation, and a persistent desire to abandon the strict plan .md protocol staffers had designed.
The human had to act as a rigorous manager, constantly steering the genius-level intuition of the machine back onto the tracks. It is a cyborg achievement, human guardrails forcing machine deduction.
Knuth notes the timeline. Delicious success for Odd May at exploration number 31 came about 1 hour after the session began. But he points out that the even numbers remain an open problem. When staffers tried to force Claude to solve the even case, Claude became disoriented, eventually losing the ability to even write syntactically correct code.
This perfectly illustrates the boundary of the AI's capability at that moment. The odd case relies heavily on the modulo skipping loop we discussed. In an even grid, that symmetry fundamentally breaks. The topological space is vastly more hostile. The AI recognized that its tools weren't working, but it lacked the deeper structural leap required to invent a new geometry for the even case. It hit its cognitive ceiling and degraded into confusion.
We have discussed the friction of the prompt engineering process, the 1-hour timeline for the odd solution, and the cognitive ceiling Claude hit when attempting the even grids. Completeness check. Does this complete our understanding of the human-AI collaborative process?
The realities of the workflow and the limitations of the model during the initial experiment are fully established. We are now ready to enter the rapid-fire developments detailed in the postscripts.
The postscript section of this document reads like a real-time log of the scientific method being massively accelerated by a global network of researchers and competing AI models. On March 3, Stappers wrote me as follows. Claude spent the last part of the process mostly on making the search quicker instead of looking for an actual construction. After I suggested to use the OR tool's CPSAT to find solutions, progress was better.
OR Tools CPSAT is a highly specialized constraint programming solver from Google. Stappers noticed Claude was wasting compute cycles trying to invent mediocre search algorithms. He intervened, acting as a high-level system architect, and prompted Claude to stop searching and instead formulate the problem as a constraint map that could be handed off to a deterministic, specialized tool. It demonstrates the shift from AI as a monolithic solver to AI as a component in a complex multi-tool pipeline.
The very next day, March 4, the scope explodes. Ho Boon Swan in Singapore wrote as follows. I have code generated by GPT-5.3 codex that generates a decomposition for even M $8. I tested it for all even M from 8 to 200 and bunch of random even values between 400 and 2000, and it looks good. Knuth interjects his own shock. Wow, the graph for MA equals 2000 has 8 billion vertices.
The even case, which broke Claude's logic, is cracked heuristically by a different researcher using a competing model, OpenAI's GPT-5.3 codex. Generating a structural path through an 8 billion vertex space without a single collision is an astonishing feat of computational power. However, Ho Boon Swan admits that the logic generated by the model is highly chaotic, making it incredibly difficult to prove its correctness mathematically by hand. It works, but they don't know why it works universally.
While the even case is being explored empirically, the rigor of the odd case is being automated. Postscript, Kevin Buzzard just told me that Kim Morrison from the Lean community quickly formalized my proof that Claude's construction is correct.
Lean is a formal proof verification language. Human mathematicians translate their logical arguments into a rigid syntax, and the computer checks every single deduction against foundational axioms to ensure absolute zero human error.
Knuth jokes in the text that he's getting more error-prone in his age, so he's relieved the machine verified his logic.
But think about the loop here. An AI generated the algorithm, a human wrote the natural language proof, and another algorithmic system formally verified the human's proof. The boundaries between human and machine mathematics are dissolving.
And the refinement of the algorithm continues. Maximilian Reitbauer has found a new construction for odd M that is probably the simplest possible. We can get a valid decomposition by replacing lines 8-10 of the Thie program. Notice that this solution uses only S and J, not I. Furthermore, the identity permutation 0-1 is used at almost every step.
Reitbauer managed to find one of the other 760 solutions, and it is vastly more elegant. It completely removes the need to track the I-coordinate, reducing the complexity of the tripwires. But how he found it is the real story. Knuth writes that Reitbauer achieved this by pasting text back and forth between GPT 5.4 extended thinking and Claude 4.6 sonnet thinking.
He used humans as manual biological routers between two competing neural networks.
Exactly. He took the context and outputs from OpenAI's model and fed them as prompts into Anthropic's model, using the strengths of each to critique and refine the other. It is the precursor to fully automated multi-agent collaboration.
We've covered the introduction of specialized solvers like OR tools, the massive empirical breakthrough for even numbers by GPT 5.3 codex, the formal verification in Lean, and the manual cross-prompting that led to a simpler algorithm. Completeness check. Are we clear on the sequence of these rapid-fire postscripts?
The explosion of decentralized, multi-tool, multi-model research is fully unpacked. We are ready to look at the final resolution of the paper.
Knuth writes, breaking news. The problem for even values of M is no longer in doubt. First, I heard again from Ho Boon Swan, who exercised the newly released GPT 5.4 Pro. Ho asked the model to look at the chaotic algorithm it had generated for the even numbers and rigorously prove it. Knuth reports the result. The result was a beautifully formatted and apparently flawless 14-page paper containing the desired exposition and proof. Ho said this was entirely the machine's doing. He didn't have to edit the paper in any way.
I want you to truly process what is written here. A 14-page, rigorous, formal mathematical proof, generated entirely by a machine in a single shot. requiring 0 human edits. To solve a previously open topological problem, the AI has completely traversed the scientific pipeline. It conducted the empirical search, formulated the algorithmic rule, generated the structural pure math deduction, and finally formatted it into flawless academic exposition. The human was reduced to pressing enter.
Finally, the loop is completely closed by Keston Aquino-Michaels, who brought these studies to a fitting conclusion. Keston eliminated the human router entirely. He built a software framework where GPT and Claude could communicate directly with each other. The result was yet another valid decomposition for the case of odd-mittance, together with an elegant decomposition for the case of even-M that's considerably simpler. His paper includes a careful analysis of how such joint interaction worked.
We have arrived at the destination. Fully autonomous, multi-agent AI research frameworks. The machines are prompting each other, critiquing each other's logical flaws, iterating on each other's code, and discovering elegant simplifications to deep mathematical truths, all without a human in the loop.
Knuth recognizes the finality of this moment in his sign-off. Over and out. We are living in very interesting times indeed. But please do not write to me with further thoughts about the topics considered here. Please work with like-minded researchers as much as you can, but without putting me into the loop. I absolutely must get back to writing 3, which will soon contain further stories of a completely different kind. He signs off with, "May the force be with you."
It is a profound, deeply human exit. Knuth, a titan of 20th and 21st century computer science, acknowledges the epochal shift. He gives his blessing to this new era of multi-agent, machine-driven mathematics, and then gracefully steps away. He asks to be removed from the loop so we can return to the human-scale stories and problems he wishes to tell. He understands that the machinery of mathematical discovery has evolved beyond the scope of a single mind.
We have covered the 14-page, zero-edit AI-generated proof, the culmination of the multi-agent framework, and Knuth's definitive historic sign-off. I'll issue our final completeness check here. Have we completed our execution of the unabridged protocol on the entirety of the source document?
The protocol has been strictly followed. Every line, every logical transition, and every mathematical concept has been thoroughly unpacked. The chain of comprehension is complete.
As we finally step back from the microscope, let's take a breath and recap the monumental journey we've just taken. We started with a highly constrained problem in graph theory routing 3 perfect Hamiltonian cycles through a toroidal 3D grid.
We watched an AI, Claude Opus 4.6, struggle through brute force, abstract the problem using group theory, hit the limits of statistical simulated annealing, and then perform a metacognitive leap into pure mathematical deduction, collapsing a 3D search space into a simple 1D logical rule.
We then watched the global research community rapidly iterate on that discovery, moving from manual prompt engineering to cross-model pasting, culminating in fully autonomous multi-agent systems generating flawless 14-page academic proofs for the entirety of the open problem.
For you listening, the hope is that you realize you didn't just spend this time learning about a niche math puzzle. You just walked step by step through the fossil record of a paradigm shift. You saw the friction, the dead ends, and the glorious realization that we need pure math. This document maps the exact coordinates of the transition from human-driven mathematical discovery to human-guided, machine-driven deduction.
And that leaves us with a lingering, provocative thought to mull over. It's a question that isn't answered in Knuth's paper, but it hangs heavy in the air after dissecting it. If an artificial intelligence network can independently formulate an algorithm, prove its universality, and generate a flawless 14-page mathematical paper that a titan like Donald Knuth accepts without a single edit, what happens to the human role in mathematics?
Are we currently transitioning from being the heroic solvers of the universe's absolute truths to merely serving as the verifiers and prompt engineers for the machines doing the actual exploring?
Who truly gets the credit for the next great theorem? The human who defined the parameters of the search space, or the multi-agent machine network that deduced the logic to traverse it?
It is a question that challenges not just the future of computer science, but the fundamental definition and future trajectory of human intellect itself.
Thank you for embarking on this intense, highly detailed deep dive with us. It was an absolute privilege to unpack such a historic, complex document for you. Until next time, may the force be with you on your own deep dives into the unknown. Welcome to the deep dive. We have got a truly fascinating one for you today.
We really do.
But before we jump in, we need to establish the ground rules for today's deep dive. because we are doing something highly experimental.
Very experimental. We are operating under what we call the unabridged protocol.
Right, the unabridged protocol. So what does that mean for you listening? It means we are going to proceed strictly line by line.
Page by page.
Exactly. Through today's source material.
Right.
We are operating under the illusion of infinite time. So we will deliberately slow down our pacing.
Yeah.
We will not skip anything.
And crucially, we have a completeness check mechanism.
Yes. Explain how that works.
Right. So after every single paragraph or after any complex formula, we will explicitly pause. We will verify with each other that absolutely no nuance has been missed before we even think about moving on to the next sentence.
So it is extreme granularity. We leave no stone unturned.
Exactly.
Okay, so let's introduce the source material. We are looking at a document titled Claude's Cycles,
By the legendary Don Knuth from the Stanford Computer Science Department.
dated February 28th, 2026, with revisions up to March 6th, 2026.
And this document is basically a real-time historical record of a paradigm shift. It is an open mathematical problem solved by Anthropic's Claude Opus 4.6.
Followed by other models, which signals a profound shift in generative AI's capacity for automatic deduction.
Right, but before we get to the AI, we need to talk about Don Knuth. We need a foundational digression here.
Yes, because you really need to understand who this guy is to grasp the weight of this document. He is basically the patron saint of computer algorithms.
I mean, he created TeX. For anyone who doesn't know, TeX is the digital typesetting system that virtually all mathematicians and physicists use to write their equations today. He invented it in the 70s because he was unhappy with how his books were being printed.
He took a decade off just to invent the way we display math on a computer. And his book, The Art of Computer Programming, is the foundational text of computer science. He's a titan.
A literal titan of the field.
Okay, so that covers our introduction to the document's metadata and our methodology. Have we missed any nuances?
I think we've thoroughly unpacked the premise and the ground rules. Let's proceed to the first paragraph.
Great. So paragraph 1, Knuth's revelation. He literally opens with shock, shock.
Which is wild coming from him.
Right. He says he was working on this open problem and then realizes Claude Opus 4.6 solved it.
And you have to look at the rhetorical weight of his next sentence. He admits he has to revise his opinions about generative AI.
From a guy who demands absolute, uncompromising mathematical rigor, that is a massive concession. He's approaching this with pure scientific joy, though. No defensiveness.
He's just thrilled the boundaries of knowledge expand it.
Okay, that covers paragraph 1 and Knuth's initial shock. Have we missed any nuances here?
I think we've thoroughly unpacked his reaction. Let's move to paragraph 2.
Okay, paragraph 2. This is where the open problem is defined.
And we need another digression here to explain the foundation. What exactly is a directed graph?
Or direct.
Right, Tiga graph. Imagine a map of a city for you listening, but every single street is a strict one-way road.
Right, you can't go backwards.
The intersections are the vertices, and the one-way roads are the directed arcs. So a directed Hamiltonian cycle is a specific kind of route through this city.
You have to start at your house, visit every single intersection in the entire city exactly once.
Exactly one.
And then return right back to your house, following only the one-way rules.
And Knuth is looking for a general decomposition of the arcs into 3 directed cycles.
It means painting the roads 3 different colors, say red, blue, and green, where each color forms its own perfect Hamiltonian cycle, and you use every single road exactly once across all 3 colors.
Precisely. Now we need to execute the perfect pronunciation protocol for the math he introduces here.
Right. So first we have the expression type, the number of vertices. The latex is M3 minor cubed.
Next, the expression type, the vertex coordinates. The latex is 0i, jj, km, 0 is less than or equal to I, j, and k, which are strictly less than m.
Then the expression type, the 3 outgoing arcs. The latex is I plus jk, ij plus k, ijk plus I plus jk, ij plus k, and ijk plus.
And finally, the expression type, the modular addition definition. The latex is I plus 1, b mod m I plus equals the quantity I plus 1 modulo m.
Okay, so the why mandate here. Why this specific hypertorus graph?
Knuth explains it's a decomposition problem for a future volume of the art of computer programming. He wants a pedagogical exercise. He needs to know if this specific 3D wrapping grid can always be sliced into 3 infinite loops for any size grid.
It covers paragraph 2 and the strict definition of the problem. Have we missed any nuances?
I think we've thoroughly unpacked the graph mechanics. Let's proceed to paragraph 3.
Paragraph 3 discusses prior human progress. Knuth himself solved it for m equals 3.
Right, a 3 by 3 by 3 grid, 27 intersections.
And his friend, Philip Stappers, empirically solved it for grids from 4 up to 16 using a computer program.
Which leads to a logical deduction. Because Stappers found solutions up to 16, Knuth notes it's highly likely they exist for all sizes greater than 2.
It proves the universe isn't playing a trick on them. The pattern holds as complexity explodes, so there must be a universal mathematical law underneath.
Okay, that covers paragraph 3 and the human baseline. Have we missed any nuances? I think we've thoroughly unpacked it. Let's move to paragraph 4, and the AI enters the chat.
Yes, paragraph 4, the prompt. Philip Stappers gives the problem to Claude Opus 4.6, but he sets very strict rules.
He forces the AI to use a file called plan.md.
He tells it, you must update plan.md after every single exploration run immediately. No exceptions.
Which is a brilliant human-AI interaction strategy.
Why is that? What's the why here?
Because of context degradation. As an AI generates tokens, its context window fills up. It basically suffers from short-term memory loss during long tasks.
So Stappers is forcing it into a structured episodic memory loop.
Exactly. By forcing it to write a summary to a persistent text file, the AI can constantly read its own diary to remember what failed and what worked. It prevents it from running in circles.
That covers paragraph 4 and the prompt engineering. Have we missed any nuances?
I think we've thoroughly unpacked the plan.md constraint. Let's look at paragraph 5.
Okay, paragraph 5. Claude's reformulation. The AI instantly reframes the problem.
Right, let's do the perfect pronunciation protocol here. We have the expression type, the required permutation function. The latex is sigma, ZM3 to S3 sigma maps, ZM cubed to S sub 3.
We need a digression on this. What are ZM3 and S3?
ZM3 is the three-dimensional grid wrapping around like a torus. S3 is the symmetric group of permutations of 3 elements.
So there are 3 colors of roads leaving an intersection and 3 possible directions.
Right. There are exactly 6 ways to assign those. The AI realizes it doesn't need to trace lines. It just needs an algebraic mapping function to spit out a traffic rule at every intersection. It turns graph theory into an algebraic mapping problem.
That is a massive conceptual leap.
It really is. And then it tries simple linear and quadratic variants for that function, but they fail. The universe is not that simple.
That covers paragraph 5 and the algebraic reformulation. Have we missed any nuances?
I think we've thoroughly unpacked the permutation mapping. Let's proceed to paragraph 6.
Paragraph 6. Exploration 2. The AI tries a depth-first search, or DFS.
A DFS means picking a path and going as deep as possible until you hit a wall, then backing up one step and trying another route.
But Claude logs that the search space is 6 to the 27th power.
Which is a combinatorial explosion. 6 to the 27th is roughly 10 to the 21st power. It's too vast without pruning.
The AI realizes brute force is impossible and aborts it.
That covers paragraph 6 and the failure of DFS. Have we missed any nuances? I think we've thoroughly unpacked the combinatorial explosion. Let's proceed to paragraph 7 and 8.
Okay, paragraph 7 and 8. Serpentine analysis. The AI looks at a 2D slice instead of 3D.
And it recognizes it as a Cayley digraph.
Time for the pronunciation protocol. First, the expression type, the 2D sequence. The latex is 0 meter, 1 meter. The sequence consisting of 0 repeated m minus 1 times, followed by a 1, with this entire block repeated m times.
Next, the expression type. The Cayley digraph. The latex is K, ZM2, E01. The Cayley digraph of ZM squared with generators E0 and E1.
So, digression time. What is a Cayley digraph and what are generators?
A Cayley digraph visualizes an abstract mathematical group. The intersections are group elements and the generators are the strict rules to move between them, like move 1 block north or move 1 block east.
And Claude formally categorized the 2D slice this way and found a serpentine pattern that perfectly solves it.
It also output a typo where it wrote modular Emery gray code, which Knuth caught as a slight hallucination, but the math was solid.
Okay, that covers paragraphs 7 and 8 on the 2D simplification. Have we missed any nuances?
I think we've thoroughly unpacked the Cayley digraphs. Let's proceed to paragraphs 9 through 12.
Paragraphs 9 to 12, the fiber decomposition.
This is brilliant. The AI realizes the 3D space is too messy, so it slices it.
Pronunciation protocol time, the expression type, the fiber coordinate map. The latex is S, I plus J plus K. B mod MS equals the quantity I plus J plus K modulo M.
So the why mandate. Why slice the graph into fibers?
Because every step on a road adds exactly 1 to exactly 1 coordinate, which means your total sum, your slice S, always increases by exactly 1.
Right. It reduces dimensionality. You're just jumping from layer A to layer B.
But the AI struggles here. It finds that the leftover roads, the residual digraphs, are too rigid to pull more cycles out of.
That covers paragraphs 9 through 12 and the fiber concept. Have we missed any nuances? I think we've thoroughly unpacked the dimensional reduction. Let's proceed to paragraphs 13 and 14.
Paragraphs 13 and 14. Exhaustive search and simulated annealing.
Exploration 18 uses exhaustive backtracking for m equals 3 and solves it in 0.1 seconds. But for m equals 4, it uses simulated annealing.
Digression. Simulated annealing, or SA. How does this mimic metallurgy?
When you heat metal, atoms bounce wildly. As it cools, they settle into a perfect low-energy lattice. In algorithms, heat lets the search take illogical uphill steps to escape shallow craters or local minima. As it cools, it settles into the deepest valley, the global minimum.
So it avoids getting stuck in local traps, and it finds a solution for size 4.
That covers paragraphs 13 and 14 on heuristic searches. Have we missed any nuances? I think we've thoroughly unpacked simulated annealing. Let's move to paragraphs 15 through 17.
Paragraphs 15 to 17. The pivot to pure math.
Explorations 21 to 29. Claude realizes SA is a dead end for a universal rule. It explicitly logs, need pure math.
It tries a single hyperplane plus rotation approach. Basically, make one route and rotate the map twice.
But it fails, and Claude proves mathematically that it must fail. It accepts the truth and kills its own darling.
This is a profound moment of machine self-correction, transitioning from empirical heuristics to abstract logic.
That covers paragraphs 15 through 17. Have we missed any nuances? I think we've thoroughly unpacked the pure math pivot. Let's move to paragraph 18.
Paragraph 18, the single coordinate realization. Exploration 30.
Claude looks at its SA data and notices a pattern. The choice at each fiber depends on a single coordinate.
When S equals 0, the choice only depends on J. When S is 1 or 2, it only depends on I.
And in Exploration 31, it writes a concrete Python program. It works perfectly for grid sizes 3, 5, 7, 9, and 11.
The AI literally writes hooray in the log.
That covers paragraph 18. Have we missed any nuances? I think we've thoroughly unpacked the coordinate simplification. Let's move to paragraphs 19 and 20.
Paragraphs 19 and 20. Deconstructing the C code. Knuth simplifies Claude's logic into C code.
Extreme granularity here. We have to break down the I-false logic line by line.
Right. The code assigns permutations like 0, 2 or 2, 10, and it swaps these permutations at the boundaries, specifically when S equals 0 and S equals M minus 1.
Why? Because by reading different digits of a string with 3 unique numbers, the 3 routes are guaranteed to never collide. Swapping them at the edges prevents closed loops that are too short.
It forces the paths to wander the entire city.
That covers paragraphs 19 and 20 on the C code logic. Have we missed any nuances? I think we've thoroughly unpacked the boundary swapping. Let's proceed to paragraph 21.
Paragraph 21. Philip Stappers tests the AI's logic. He runs it for odd M up to 101.
Over 1 million vertices. Flawless. The problem is empirically solved for odd M.
That covers paragraph 21. Have we missed any nuances?
I think we've thoroughly unpacked the verification. Let's move to paragraphs 22 through 26.
Paragraphs 22 to 26. The bumping rules. Knuth translates the AI code into human English.
Right, the specific rules for the first cycle. For example, when S equals 0, bump I if J is M minus 1, else bump K.
Bump simply means increase by 1 modulo M.
And we need the pronunciation protocol here for the cycle progression, the expression type, the cycle progression. The latex is 0 to 2 to 002 to 1002, 2 transitions to 002, transitions to 000.
Knuth writes out 125 steps for humans to see the rhythm.
That covers paragraphs 22 through 26. Have we missed any nuances? I think we've thoroughly unpacked the bumping translations. Let's proceed to paragraphs 27 through 31.
Paragraphs 27 to 31, proving all M-cubed triples occur.
This requires extreme granularity. Knuth proves that triples for the same S are spaced exactly M steps apart.
Right, because every step adds 1 to S. It takes M steps to cycle back to the same slice.
And he tracks a variable K. He finds that every M steps, K is increased by exactly 2 modulo M.
The Y mandate. Why does M needing to be odd matter here?
Because if M is even, say, 4, adding 2 modulo 4 goes 0, 2, 0, 2, an infinite subloop. You miss half the coordinates.
But if M is odd, say 5, adding 2 modulo 5 goes 0, 2, 4, 1, 3, 0, it perfectly sweeps the entire range because 2 and odd numbers are coprime.
That simple number theory fact is the master key to the proof.
That covers paragraphs 27 through 31 and the formal proof. Have we missed any nuances?
I think we've thoroughly unpacked the coprime necessity. Let's proceed to paragraphs 32 through 37.
Paragraphs 32 to 37. Claude-like decompositions.
Knuth looks for a generalizable Hamiltonian cycle.
Pronunciation protocol time. The expression type. The generalized coordinates. The latex is I-E-T, J as 80, S-E-T as S-I-J. The mode 3I equals I prime, J equals J prime, S equals S prime, and K equals the quantity S minus I minus J modulo 3.
Knuth maps it to an exact cover problem. Out of 11,502 cycles for m equals 3, he finds 760 are Claude-like.
Meaning they are valid for all odd m greater than 1.
The irony here is thick. Claude Opus 4.6 mathematically bled to find just one needle in this infinite haystack, and Knuth analyzes the needle and finds a pile of 760 identical ones.
He even says the one Claude found wasn't necessarily the nicest.
That covers paragraphs 32 through 37. Have we missed any nuances? I think we've thoroughly unpacked the 760 decompositions. Let's move to paragraphs 38 through 41.
Paragraph 38 to 41. The reality of the AI session.
It wasn't magic, it was a grind.
Philip experienced tons of friction. The AI stopped on random errors, lost results, and needed constant reminders to use the plan.md file.
And when Philip asked it to solve the even values of m, it completely broke down.
Right, it got stuck and lost its ability to even write basic Python code correctly.
This is agentic fatigue. In long autonomous tasks, the context window fills with negative results and the LLM loses its reasoning coherence.
That covers paragraphs 38 through 41 and the human-AI friction. Have we missed any nuances?
I think we've thoroughly unpacked agentic fatigue. Let's proceed to the appendix.
Okay, the appendix. Knuth briefly includes the bumping rules for cycles C equals 1 and C equals 2, just for completeness.
That covers the appendix. Have we missed any nuances? I think we've thoroughly unpacked it. Let's look at postscript 1.
Postscript 1, dated March 3. Philip Stappers tries again with even numbers, but he uses OR tools CPSAT.
Which is Google's open source toolkit, digression time. What is CPSAT?
Constraint programming.
Right. It's completely different from simulated annealing. It's declarative. You just state the unshakable rules like paths cannot overlap.
And the inference engine instantly prunes mathematically impossible paths without testing them, so it found even M solutions in seconds.
That covers postscript 1. Have we missed any nuances? I think we've thoroughly unpacked constraint programming. Let's look at postscript 2 and the post-postscript.
March 4th. Ho-Boon Swan uses GPT 5.3 codex to generate a decomposition for even m greater than or equal to 8.
The scale is insane. For m equals 2,000, that yields 8 billion vertices.
And Kevin Buzzard notes that Kim Morrison formalized Knuth's proof in Lean.
Digression, what is Lean?
It's an interactive theorem prover.
Modern math proofs are so dense that human peer review is failing. Lean forces a computer to strictly check every logical deduction. If it compiles, it's undeniably true. It's the ultimate check on human and AI error.
And Max Reitbauer uses GPT 5.4 and Claude 4.6 Sonnet together to find an even simpler construction for odd m.
That covers the second postscript. Have we missed any nuances? I think we've thoroughly unpacked Lean and the model escalation. Let's look at the breaking news.
Breaking news. Even m is rigorously solved. Ho-Boon Swan used GPT 5.4 Pro to generate a flawless 14-page proof entirely autonomously.
And Keaston Aquino-Michaels used a multi-agent structured exploration with GPT and Claude to find an elegant even M decomposition.
The acceleration is terrifying. From Feb 28 to early March, we went from an open problem to AI heuristics to human proof to autonomous AI-generated 14-page formal proofs.
That covers the breaking news. Have we missed any nuances? I think we've thoroughly unpacked the timeline acceleration. Let's move to the outro.
The outro. Knuth's final sign-off. He writes, "Please do not write to me. I absolutely must get back to writing Volume 4A.
It's hilarious. After documenting a massive AI disruption, he just wants to be left alone to finish his book.
A very human desire." That covers the final paragraph. Have we missed any nuances?
I think we've thoroughly unpacked the entire unabridged document.
So we wrap up this massive journey, but we want to leave you, the listener, with a final provocative thought.
Based on this document, we watched AI transition from brute force guessing to mathematical intuition to multi-agent peer review, and finally to writing flawless 14-page formal proofs in just a matter of days.
Right.
So if an AI can now dynamically shift between empirical search and abstract conceptual leaps.
And formally prove its own work.
Exactly. What becomes the role of human mathematical intuition? Are we simply becoming the managers of digital savants, taxed only with asking the right questions? Or will our fundamental definition of understanding have to evolve?
Something to mull over. Thank you for surviving the unabridged protocol with us today. Keep questioning, and we'll see you in the next deep dive.
What if you were a total legend in your field, a true giant, and you wake up one morning to find out an AI just solved a problem you've been wrestling with for weeks? Well, that's the incredible story we're diving into today, and it's all documented by the great Donald Knuth himself.
So here's the game plan. First, we're going to feel that initial shock of the discovery. Then, we'll follow the AI's breadcrumb trail as it finds a solution for odd numbers. After that, we'll see how that solution was actually proven and figure out what happened with the other half of the problem, the even numbers. And finally, we'll look at how this whole thing just kicked off a brand new era of discovery.
All right, let's set the scene. This whole thing kicks off with a real shocker to one of the biggest names in computer science, Donald Knuth. He's writing about this, and he even sets it in the near future, 2026, when he gets completely blindsided. I mean, look at this quote. Shock, shock. This is not just, oh, that's interesting. This is a full-blown paradigm shift. When a mind like Donald Knuth's is this rattled by an AI's creative jump, you know we've crossed some kind of new frontier in automated thinking. All right, so let's open up the case file. What exactly was this problem? What was this puzzle that could stump a genius but get cracked by a machine? Well, it's all about something called a directed Hamiltonian cycle.
Okay, first things first, let's get the lingo down. We are dealing with something called a digraph. The easiest way to think about it, it's like a city map, but every single street is one way. You can only go where the arrows point.
So here are the rules of the game. Picture this cube of points in space. From every single one of those points, you have 3 one-way streets leading out. And the challenge? You have to find 3 perfect, separate, non-overlapping loops that hit every single point exactly one time. It is, no joke, a massive, cosmic-level game of connect the dots. Now, this problem didn't just pop out of thin air. Knuth himself had actually solved a tiny version of it. He then threw down the gauntlet, making the general problem an exercise in his famous book. Then, a researcher, Philip Stappers, comes along and finds solutions for a few more cases, which kind of proved a general solution had to be out there. And that's when Stappers had this brilliant, game-changing idea. Hey, why don't I just ask the new AI?
And this, my friends, is where the detective story really kicks into high gear. Because Stappers didn't just tell the AI to go solve it. He gave it one single, absolutely crucial instruction.
Yeah, this one. After every run, immediately update this file, no exceptions. This little command is the whole reason we're here. It forced the AI to keep a detailed diary of its entire thought process, giving us this incredible, unprecedented peek inside a non-human mind as it tackles a seriously complex problem. So what did Claude do first? Well, it started with the usual computer science playbook. It tried simple functions. Nope. It tried a brute force search. Way too slow. It even had some really clever ideas, analyzing patterns and structures. But everything it tried just hit a dead end, a brick wall.
So, you get the picture, right? The standard toolkit is just not cutting it. The AI has to do something different. It has to get creative. It can't just run through known algorithms. It needs a real, honest-to-God conceptual breakthrough.
And bingo, here it is. In exploration number 15, Claude completely reframes the problem. Instead of staring at this big 3D cube, it decides to slice it up into 2D layers, which it calls fibers. And this is the takeaway, right? Sometimes the only way to crack a problem is to stop looking at it head-on and come at it from a totally different angle. So, with this new fiber perspective, Claude suddenly starts making progress. It's finding solutions for the smaller cubes using different search techniques. It was getting answers, which is great, but it still hadn't found the magic formula, the universal key that would unlock all the cubes. And this right here, this is a wild moment of what looks like self-awareness. The AI basically says, okay, search algorithms can find individual answers, but they can't give me the general rule. I need pure math for that. It recognizes its own limitations. It knows that brute force isn't enough. It needs a more elegant, abstract insight. Then, Claude has this incredibly elegant idea. It's so beautiful. What if I just create one perfect cycle and then just rotate it to get the other two? And you know what? It almost worked, but it failed right at the edge at a very specific mathematical boundary. And that failure was actually super important because it proved that a simple, perfectly symmetrical answer just wasn't going to work. So where did the real breakthrough come from?
Well, Claude went back and started studying one of its own solutions that it had found earlier, and buried inside, it found a hidden pattern. The logic it needed to choose the next step was way simpler than it had imagined. This tiny, subtle observation, that was the key that unlocked the whole thing. And that one subtle pattern, that was everything. It was all the AI needed to finally build a general solution that worked for all the odd-numbered cubes.
And there you have it, the eureka moment. After plugging its new insight into a program and running the tests, Claude gets the confirmation. Perfect decomposition. It had done it.
And the solution itself, the final artifact, it can be boiled down to this really elegant, compact piece of C code. When you look at it from a high level, it's really just a simple loop that builds each of the 3 giant cycles, one after the other.
So what's the logic here? How does it actually work? Well, it's pretty wild. At every single point in this massive graph, the algorithm just asks itself a simple question. What layer am I on? And based on the answer to that one question and where it is on that layer, it knows exactly which of the 3 paths to take next. It's a simple, local rule that somehow creates this perfect global tour.
And what's really cool is that the rule isn't exactly the same everywhere. It changes just a little bit depending on whether you're on the very first layer, the very last layer, or somewhere in the middle. It's this incredible combination of simplicity and nuance that makes it all work. Okay, but here's the thing. A computer program that runs and gives you the right answer is not a mathematical proof. Not even close. You need rigor. You need certainty. And that's where the legend, Donald Knuth, steps back into the story. He took the AI's code and set out to prove, mathematically, that it was undeniably correct. So Knuth's job was basically to be a translator. He had to take the AI's programming logic and translate it into the formal language of mathematics, a clear step-by-step recipe that any mathematician could follow to create these 3 enormous loops.
And check this out. When you actually take that recipe and apply it to the smallest odd-numbered case, you can literally trace the path. It just works. It methodically visits all 27 points, never repeating, before linking up perfectly back at the start. The logic is solid.
So here's the million-dollar question. Why does this brilliant solution only work for odd numbers? Well, the heart of the proof is this incredible gearing mechanism. Every time the path completes a full tour of the cube, one of the key coordinates gets bumped up by 2. Now, because the number of layers is odd, this process of stepping by 2 is guaranteed to eventually land on every single layer. It's a mathematical certainty. And then Knuth's analysis revealed something totally unexpected, a little twist in the story. The AI didn't find the solution. It found one solution. In fact, there were at least 760 different valid ways to solve this problem. An entire family of correct answers was just sitting there, waiting to be found. So, okay, the case for odd numbers, slam dunk, closed, proven. But what about the other half of the problem, the even numbers? Well, this is where the story takes another really interesting turn.
So after this massive win, Philip Stappers asked Claude to go back and tackle the even-numbered cubes. And it just couldn't do it. It started spitting out errors. It couldn't even run its own programs correctly. It just broke. It's a really important reminder that these incredibly powerful models can also be surprisingly brittle. That flash of genius, it couldn't just summon it again on command.
But here's the thing. The failure of that one AI wasn't the end of the story, not by a long shot. In fact, it was just the beginning. Once Knuth published this whole saga, it kicked off an absolute firestorm of activity in the research community.
I mean, just look at this timeline. It is absolutely breathtaking. In a matter of days, not years, but days, the entire rest of the problem gets solved by a different AI. The original proof for the odd case gets formally verified by a machine. A human researcher finds a simpler solution, and then another AI writes a full 14-page proof for the new solution. This isn't just science. This is science moving at the speed of light.
And look at how elegant this is. Inspired by the AI's breakthrough, a human researcher found an even simpler, more beautiful solution. It's a perfect example of human intuition taking an AI's discovery and refining it, polishing it into something closer to mathematical perfection.
Donald Knuth's own takeaway from this whole whirlwind of events really just says it all, doesn't it?
So, we'll leave you with this question. This story isn't really about one AI solving one math problem. It's a glimpse into the future. It's a preview of a whole new way of doing science, where humans act as guides, AIs go out and explore the wilderness, other AIs come along to verify the findings, and this global community just accelerates discovery at a pace we've never, ever seen before. What comes next? The possibilities are just staggering. All right, you've got to hear this story. It seriously sounds like it's pulled straight from a science fiction movie, but I promise you, it's 100% real. It's about a problem that had one of the greatest minds in computer science completely stumped, and the hero that came out of nowhere to solve it was an AI. This is about way more than just code. It's about witnessing the dawn of a whole new way of making discoveries.
I mean, listen to this. You just don't hear the word shock, let alone twice, from Donald Knuth. This is a titan, a living legend. The guy who wrote the literal Bible of computer science, the art of computer programming. So when he says something like that, you know something absolutely massive just happened. He was weeks deep into a really thorny problem, only to find out an AI he'd never even heard of had already cracked it.
So, to really get why this is such a big deal, we need to understand the challenge itself. This whole thing started with a puzzle Knuth was wrestling with for one of his upcoming books. It's a problem of pure, beautiful, but incredibly complex mathematical structure. He had a feeling there was a solution, but he needed a universal rule, something that would work every single time, no exceptions.
Okay, let's break this down. Imagine a gigantic, multi-dimensional hotel with millions, maybe billions of rooms. It's weird. And from every single room, there are exactly 3 specific one-way doors that lead to 3 other rooms. Now, here's the challenge. Can you find 3 completely separate tours that visit every single room in that hotel exactly one time, using all the doors? It is a brain-meltingly complex puzzle.
Now, before any AI got involved, a human was already on the case. Knuth's friend, a computer scientist named Philip Stappers, basically just rolled up his sleeves and started grinding. He managed to find solutions for a bunch of specific sizes of the hotel, from a small one with 64 rooms all the way up to one with over 4,000. So this proved it was possible, but that magic key, the general rule for any size, was still completely missing.
And this, right here, is where our main character enters the story. It wasn't some rival mathematician or a big university research lab that picked up the gauntlet. Nope, it was an AI. Philip Stappers just decided to see what would happen if he asked the machine for help.
And this wasn't as simple as just typing in a question and getting an answer. You have to think of Stappers as a guide, or maybe a coach. He gave the AI Claude the exact problem description from Knuth. And then he did something absolutely crucial. He told it to keep a detailed journal of its entire thought process. Every idea, every dead end, every little breakthrough had to be written down. And what a journey that was. Claude did not just find the answer on the first try. Oh no, it struggled. A lot. First, it tried the obvious stuff. Simple formulas. That didn't work. Then it tried to just brute force it, check every single possibility, but that was hopelessly slow. It even had this really clever idea about what it called serpentine patterns, which looked promising for a minute, but that turned out to be a dead end too. So, after just hitting wall after wall, the AI came to a really interesting conclusion. It realized that its current toolkit just wasn't going to cut it. It needed a totally new perspective on the problem. It needed a real conceptual leap. And here's that leap. Claude came out with this brilliant idea it named fiber decomposition. Instead of trying to look at the whole problem as one giant, tangled-up mess, it figured out how to slice it into these neat, organized layers it called fibers. And suddenly, with this new viewpoint, the hidden structure of the problem became so much clearer. It was an absolutely genius move.
But even that amazing insight wasn't the final answer. It wasn't a magic bullet. The AI used this new way of looking at things to run a bunch of sophisticated experiments. And yeah, it could find answers for specific cases, but it still couldn't find that universal rule. The ultimate prize was still just out of reach.
And then, this is the part that is just incredible, this moment of genuine self-awareness. After its 25th major attempt, the AI itself concluded that just trying things out, no matter how cleverly, was not going to solve the problem. It recognized that it needed something more elegant, something more fundamental. It literally said it needed, quote, pure math. The machine knew it had to stop thinking like a computer and start thinking like a mathematician.
So, after putting on what Don Knuth later called its new thinking cap and focusing only on that pure mathematical structure, it finally happened. In the log file for its 31st big exploration,
Success. Total, undeniable success.
And Claude didn't just write down a theory or an idea. It produced a working Python program. A program that, when you run it, spits out the 3 perfect loops for any odd number you throw at it. Just like that, for half of the entire problem, the impossible quest was over.
Okay, so Claude provided the code, which is amazing. But in the world of mathematics, just having code that works isn't enough. You need the proof. You have to understand why it works. And when you actually dig into the AI's solution, you find this surprising, almost beautiful elegance.
At its heart, the solution is just a set of surprisingly simple rules. Basically, depending on your coordinates, your exact location in that giant hotel, the code tells you which of the 3 doors to go through next. And what's so mind-blowing is how these simple local rules all add up to create a perfect, complete tour of the entire structure.
And here's the secret sauce, the logic behind the magic. The program basically groups all the rooms together based on their first coordinate. Let's just call it I. The rules are set up so that you visit every single room where I equals 0 before you ever move on to the rooms where I equals 1, and so on. And because the total size, m, is an odd number, this superstructured process guarantees you make one perfect, unbroken loop. It's beautiful.
And get this, Claude's solution wasn't some 1 in a billion fluke. After seeing the answer, Knuth went back and calculated that there were actually 760 different Claude-like solutions that could solve the problem using a similar kind of logic. The AI didn't just find a needle in a haystack, it discovered a whole new way of making needles.
But believe it or not, the story doesn't stop there. So Claude had solved the puzzle for all the odd numbers, but that breakthrough, it didn't just close the chapter. It kicked the door wide open to a completely new era of collaborative science.
Just look at this timeline. The speed is absolutely breathtaking. The day after the odd numbers solution drops, Stoppers and Claude are already attacking the even numbers. The very next day, a totally different AI, GPT, spits out a working solution for the even numbers. On the same day, a human expert formalizes and verifies the first proof. Then, a couple days later, 2 different AIs collaborate to find an even simpler solution. And to top it all off, an AI then generates a full, 14-page, rigorous mathematical proof all by itself. This is an absolute cascade of discovery. And that's really the big takeaway here. The story stopped being about how clever one AI was, and it became about an entirely new way of doing science. A method where humans act as the guides, the coaches, the strategists, and different AIs act as these relentless, creative explorers, even working with each other to push the frontier forward.
Which brings us right back to the man who started this whole journey. Donald Knuth's initial shock quickly turned into a sense of wonder. And his final thought on this whole thing is both incredibly simple and deeply profound. He recognizes that we are witnessing a fundamental change in how science itself is done.
So that's the question we're all left with, isn't it? This wasn't a story about an AI just finding patterns in a huge dataset. This was an AI demonstrating creativity, course correction, and genuine mathematical insight to solve a problem that had a world-class expert stumped. So if this is what's happening today, what comes next? What other great unsolved problems are just waiting to be cracked?
All right, let's get into a story that honestly sounds like it's been pulled straight from the future. It's got everything. A puzzle that was considered a real beast, a legend in the world of computer science, and an AI that just, well, it did something no one saw coming. You know, you really don't hear words like shock coming from Donald Knuth. This is one of the founding fathers of computer science we're talking about. So when he says something like this, you just know that the ground has shifted under our feet. And that's exactly where our story kicks off. The moment a legend realized the game had completely changed. Okay, so to really get why what this AI did is so amazing, you first have to understand the challenge it was up against. And look, this wasn't just some random brain teaser. This problem came from Knuth himself, while he was in the middle of writing his life's work. Now, for anyone who might not know, the art of computer programming is basically the Bible for any serious programmer. Knuth is famously meticulous, and this whole puzzle grew out of his deep dive into something called directed Hamiltonian cycles. You can think of that as just a fancy term for trying to find one perfect one-way trip through a super complex network that hits every single spot exactly once. This is a great way to picture what's going on. Imagine a Rubik's Cube, but instead of colors, every little cube is just a point in space. Now, from every single one of those points, there are 3 specific paths leading away from it, kind of like one-way streets. The puzzle was this: can you find 3 giant, perfect tours that together use up every single one-way street exactly one time without any of the tours overlapping. Knuth had figured it out for a tiny 3 by 3 by 3 cube, but what he really wanted was a general rule that would work for a cube of any size. So Knuth's colleagues are also totally hooked by this problem, and it just so happened that one of them had access to a brand new tool. And here's a really important piece of the story. The AI wasn't just working on its own in some isolated server farm. A human researcher, this guy Philip Stoppers, very deliberately took this puzzle and decided to partner up with an AI. He fed it Knuth's exact problem description and told it to document every single thing it tried, just like you would with a human research assistant. What happened next wasn't some magical, instantaneous answer. Nope. It was a real investigation, complete with different strategies, a bunch of dead ends, and these little flashes of insight along the way. You know, the way Claude went about this was surprisingly human. First, it did what any good mathematician would do. It translated the puzzle into formal math. It tried the obvious thing first, a brute force search, but yeah, it figured out pretty fast that was going to take forever. So then it got creative. It started finding these cool geometric serpentine patterns. It tried slicing the cube into layers and even used this really powerful technique called simulated annealing. Now, that stuff found some specific answers, but it couldn't find that general rule that Knuth was after. This is what's so wild. It wasn't a one-and-done kind of thing. For 29 different explorations, as it called them, Claude would try a method, see it fail, figure out why it failed, and then pivot to something new. It was actually learning, just like we do. And this right here, this is just brilliant. It shows a kind of self-awareness. After trying that simulated annealing approach, it basically said to itself, okay, this method is great for finding one-off solutions, but it's never going to give me that beautiful general proof I need. I've got to switch from just number crunching to pure math. And then the breakthrough started to happen. In its 30th try, it decided to go back and look at an answer it had found for a smaller cube way earlier. And it spotted something, a tiny, subtle pattern in that old solution. It was the clue it had been missing, hiding in its own previous work. That little clue was literally all it took. That one insight from Exploration 30 led it straight to the final, beautiful solution. So on its very next try, number 31, Claude didn't just write down the answer. Oh no, it wrote a functioning Python program, a program that could spit out the 3 perfect tours for any cube with an odd-numbered side, whether it was 3 by 3 by 3 or 99 by 99 by 99. The result was just staggering. A problem that had one of the greatest minds in the history of computer science stumped for weeks was cracked, with a working program to prove it, in about an hour of the AI's time. But there was a catch. It only worked for odd-numbered cubes. The story wasn't quite over yet. See, Claude's breakthrough wasn't the finish line. It was more like the starting pistol that set off a mad dash among other researchers and, yeah, other AIs. So Claude had only solved half the problem, right? But what that did was it energized the whole community. It gave everyone a brand new, clear target to aim for: solve the puzzle for the even-numbered cubes. The timeline that followed is just, it's breathtaking. Seriously, look at this. Day 1, Claude solves the odd cases. 2 days later, a human turns that into a formal mathematical proof. The very next day, a different AI model cracks the even cases. And then, a few days after that, another AI writes a full-blown 14-page academic paper proving its own solution is correct. It's insane. What we're actually witnessing here is a totally new way to do science. You have humans guiding the AIs, giving them the big problems. Then you have AIs not just solving pieces of the puzzle, but actually building on each other's work. It's like researchers were using different AIs like different specialized tools in a workshop, playing to their unique strengths. And once that first dam broke, it just became a flood. Researchers working with these new AI partners found out that Claude's original solution was just one of over 700 similar types of solutions. They even found simpler, more elegant ways to solve the whole thing by getting the AIs to collaborate with each other. So, all of this brings us right back to the man who started it all. After this absolute whirlwind of discovery, what was his final take on everything that had just happened? Instead of being upset or feeling replaced, Knuth was just thrilled. He tipped his hat to the AI's creativity and basically said, "Welcome to the new world." He recognized that we've just entered a very, very interesting new era. So at the end of the day, the big takeaway here isn't really that an AI is smarter than a person. It's that the combination of the two is way more powerful than either one is alone. This was a landmark event. It proved a new model for how we can do research, a genuine, creative partnership between human intuition and the tireless, increasingly insightful power of an artificial mind. This story really gives us a sneak peek into a future where the pace of discovery is just accelerated beyond anything we can imagine. It leaves us with this huge question, right? If a computer science puzzle that's been around for decades can be completely cracked in a matter of days, what other giant mysteries in medicine or physics or math are suddenly within our reach?